Our second speaker for the morning session is Cornelia Drutu, and she will tell us about property T and a T-menability for Banach spaces. Please.
Right. So I'd like to thank the organizers for inviting me to speak at this conference. It's an honor. And I'd like to thank Bruce Kleiner for proving so many beautiful theorems and inspiring. I thought of this as a colloquium talk because of the various expertise of the audience, which means that sometimes it will be too slow for experts, so I apologize for that. And maybe at other times I would not define things so that people would follow. So if that is the case, please do interrupt me and ask for the definition. So the main topic is related to the following, say, general way of understanding objects, whether geometric, algebraic, or combinatorial. It's by drawing them on the right board, so to speak. And this is something that has been done a lot in theoretical computer science and combinatorial optimization. So if one wants to solve a problem, try and draw that structure, the combinatorial structure, faithfully enough on a good enough board. So in other words, embed the combinatorial structure well enough in a well-understood metric space, and then use that ambient, well-understood geometry to devise the algorithm that you want to devise. And so first of all, what is a good enough embedding? What is a good enough board? So as far as the embedding, it will be most of the time quasi-isometric embedding or coarse embedding, or uniform embedding in the usual sense. And as far as the board is concerned, well, so it's already quite obvious that the two-dimensional board has a lot of limitations, even for graphs. So for graphs, like the more complicated the graph, the larger the dimension one has to consider. So since actually this talk is going to be about infinite groups, so infinite Cayley graphs, it is natural to consider a board of infinite dimension, that is a Hilbert space. And later on, another kind of good board that I will consider will be LP spaces or Banach spaces with good properties. So maybe I'll just place myself there. And one first and impressive illustration of this philosophy is the theorem of Gouliang-Yu, who proved that if a group has a uniform embedding, so an infinite finitely generated group has a uniform embedding in a Hilbert space, then it satisfies the Korsbaum-Kohn conjecture and the Novikov conjecture. So it does work, this strategy. And there was a brief moment, I believe, where people rejoiced and thought that this might pretty much solve the problem, because one would say a priori that Hilbert space is the right board, so one can embed uniformly any finitely generated group in it. But then came the bad news, the Gromov monsters. So Gromov sketched the construction, and this was later on cleaned further by Arjantseva and Dalzan, and the result has been improved by Osaida. So there exist finitely generated groups who have families of expanders uniformly embedded in them. And that means that such groups cannot embed uniformly into a Hilbert space, and therefore this theorem does not apply. And I mean, there are there's a lot of work on this same kind of question, embeddings and testing the compatibility, the metric compatibility of infinite finitely generated groups with Hilbert spaces. In, say, one of the directions in the same spirit is another kind of metric compatibility. So what if we consider quasi-isometric embeddings of finitely generated groups into Hilbert spaces? And Cornelia, Tessera, and Valette formulated the conjecture that if a group is quasi-isometrically embedded into a Hilbert space, then it must be virtually abelian. And for instance, the proof for linear groups uses a lot of the mathematics that we all like. So first of all, so if the group is linear, one can consider that it's alternative, and there is a metric version of that it's alternative. So either a group is virtually solvable, or it contains a free subgroup. And as it turns out, it's quasi-isometrically embedded, so that reduces it to solvable groups. And then there is a metric version of Milnor-Wolf, which further reduces it to nilpotent groups. So that means that outside the class of linear nilpotent groups, there is a quasi-isometrically embedded simplicial tree in the Cayley graph, and therefore the Cayley graph cannot be quasi-isometrically embedded in a Hilbert space. And if one restricts to nilpotent groups, so let's see, if we have a nilpotent group and we consider a quasi-isometric embedding of that nilpotent group into a Hilbert space, well, first of all, we mod out by the torsion, it becomes torsion-free, we apply Maltsev, and it becomes a lattice in a Lie group. And then we consider ultra limits of this quasi-isometric embedding, and this is going to become a bi-Lipschitz embedding of what is called the asymptotic cone of the nilpotent group, which is the same as the asymptotic cone of the Lie group associated. So one gets a bi-Lipschitz embedding from this Lie group, a graded Lie group, to a Hilbert space again. And then the other important ingredient is that this bi-Lipschitz embedding, so there is a Rademacher theorem, this bi-Lipschitz embedding is differentiable almost everywhere. So then one can look at the derivative, at a derivative instead. And for the derivative has extra properties, and it is easier to show that therefore such a derivative cannot exist, and therefore the quasi-isometric embedding cannot exist. And this implies that as soon as we know that the group is nilpotent, it can only quasi-isometrically embed into a Hilbert space if it is abelian. And this is a combination of the work of several people, Sams, Cheeger-Kleiner, and Pauls. But one of the main ingredients is the theory of Cheeger-Kleiner of differentiability of maps with target Hilbert spaces. And then more importantly, they did this also for Banach spaces. And for me, the psychological shock came when they managed to do it when the target were L1 spaces. But that does not appear here. And then they use that jointly with, in joint work with Assaf Naor to answer the Guman's linear conjecture, also called the Sparsest Cut conjecture. But I'm not going to talk about that. I'm just saying that there's some beautiful math also using this sort of theory of differentiability. Now, returning on that question of representing a group accurately in a Hilbert space, one can also try to embed it equivariantly. So you want to embed it not just metrically, so the finitely generated group and the Cayley graph, but also preserving the action. So in other words, you want that embedding to be equivariant. So in other words, we are going to consider a setting where the kind of embedding of the group on the metric space that we consider is that we ask that the group acts on the metric space by isometries, and that the orbit map is a uniform embedding. So that's what I mean by equivariant metric embedding. Which uniform embedding is equivalent to the property that the action is proper in this sense. And for Hilbert spaces, this property of groups is called either the Hagerup property or a-T-menability. So the Hagerup property was the initial terminology. Only it turns out that there are a lot of Hagerup properties. And the a-T-menability terminology is introduced by Gromov. And there are two reasons for that. So one of them, for this terminology, one of them is that it is a generalization of amenability, of the amenability of von Neumann. So amenable groups are A-T-menable. But other examples of amenable groups are groups with proper actions, either or real hyperbolic spaces or complex hyperbolic spaces. So these are all A-T-menable as well. And in particular, free groups are in this class. And here again, a theorem illustrates what I said in the beginning. As soon as we have a group that has a good representation on a good space, we can say things about it. So in this case, the of A-T-menability is the theorem of Hickson-Kasparov, which is the equivariant version of Guliang-Yu's theorem. If groups are A-T-menable, then they satisfy the classical Baum-Kohn conjecture. Actually, I should say that chronologically, I'm basically going backwards because Guliang-Yu is the most recent. This is before that. And what I'll say next is actually the beginning of the story. So now we'd like to understand what is the non-compatible case in the same way in which the Grove monsters were metrically incompatible with the Hilbert spaces. Now, in the equivariant case, the strongly non-compatible case is the so-called property T of Kazhdan. So these are the groups that definitely have no reasonable representation on the infinite blackboard that is a Hilbert space. So Kazhdan property T in this setting can be formulated by the property that every action by affine isometries on a Hilbert space must have a global fixed point. Now, again, I mean, chronologically and historically, this was not the definition of Kazhdan. This was later proved to be equivalent to the property T of Kazhdan. But in any case, so these are sort of the bad news in our attempt to represent equivariantly groups on Hilbert spaces. And examples cover a lot of interesting groups, to begin with a lot of interesting linear groups like SL and Z. When n is at least 3, they have property T. More generally, what we call lattices in simple groups of rank at least 2, or lattices in semi-simple groups where all the factors have rank at least 2. Now, another source of examples are the so-called random groups. So I'll actually define one theory of random groups later, but for the moment, just imagine that we managed to introduce some theory of random groups for the class of finitely presented groups. So it's a countable class. You can imagine that we exhaust it by finite sets. And whenever yeah, so we can construct a theory of random groups, and random groups with few relations are A-T-menable, while random groups with many relations have property T. So there are a lot of groups in both classes, so both property T and A-T-menable. And now, if we want variations of this, so there are several ways in which we can construct these variations. So one of them is to replace the Hilbert spaces by LP spaces. So these are sort of the nearest relatives of Hilbert spaces in the class of Banach spaces. And another way of varying the definition of these two properties is, instead of looking at affine isometric actions, to look at affine actions that are no longer isometric, uniformly by Lipschitz, but I'll mention this later. And a general remark is that as soon as one formulates versions of property T that are stronger, one way or another, hyperbolic groups and rank 1 lattices tend to lose that property. Actually, they tend to have the opposite that corresponds to A-T-menability, while higher rank lattices tend to have that stronger property. And you will see later that this is what happens in this case as well. So if we fix any P in the class between 1 and infinity, actually it makes sense also to speak for to discuss the case of P positive, P larger than 0, but I will just restrict most of the time to this. The fixed point property is simply, we say that G satisfies this fixed point property if every affine isometric action on an LP space has a global fixed point. So it's really like what we used to have for Hilbert spaces, but it's for LP spaces. And the opposite, A-FLP-menability, corresponds to having a proper action by affine isometries on an LP space. And well, I mean, there are various reasons why these are interesting and important. So one of them is that there are some rigidity results. So in many ways, property T is perceived as a rigidity results, and having FLP leads to more rigidity. And also, because same as for the Hilbert space, A-FLP-menability implies Novikov. So this is Kasparov and Yu. So there are many reasons why these are interesting to consider. And so let's see how this fixed point property and A-FLP-menability compare with the classical ones. Actually, for P between 1 and 2, they are equivalent. So for P not 1, the equivalence is an old result of Delorme-Guichardin. For P equal to 1, it's trickier because actually Delorme-Guichardin implies that T is equivalent to every action on an L1 space has bounded orbits. But because L1 is not uniformly convex, this is not a priori equivalent to the fixed point property. So there is extra work to be done. And it's actually a theorem of Bader, Gelander, and Monod. And another thing is that actually FLP always implies T. So it doesn't matter if it is between 1 and 2 or larger than 2, it always implies T. And if P is large enough, at least, one can argue and actually show that FLP is strictly stronger. And this comes from results that go some time back. So Pierre Pensu implicitly and explicitly, Cornelia Tessera and Valette proved that if we consider the quaternionic hyperbolic space, say of dimension n, and if we look at either its group of isometries or any lattice in it, all these have property T. But on the other hand, they start acting properly on LP spaces as soon as we go with P beyond this number, which is the conformal dimension of the boundary. And the same thing happens for hyperbolic groups. So you proved that hyperbolic groups always act properly on an LP space, and Marc Bourdon actually proved that this actually happens as soon as P is larger than the conformal dimension of the boundary again. So interestingly, for hyperbolic groups, this seems to relate to a geometric feature, the conformal dimension of the boundary. And well, of course, I mean, it's interesting for groups that have property T, because so they have the fixed point property for hyperbolic groups for L2, but when we get P large enough, they fail to have it. They fall in the other category, a-T-menable. It's not clear what happens if P is small. The one thing that can be said is that one can go a little bit beyond 2 for every group. So for every group, we would know that it has the fixed point property for some 2 until 2 plus a certain epsilon, depending on G. This is due to an argument of Fischer and Margulis. And as I was already mentioning, higher rank lattices have all the fixed point properties. So in particular, SL and Z. So these, any kind of strengthening of property T, higher rank lattices will always have them. So say like this one. And this is due to Bader, Furman, Gelander, and Monod. So this is one version. And actually, I should also mention that instead of LP spaces, one can consider uniformly convex Banach spaces, or some subclass called uniformly curved, but I'll mention that later. Another way of varying property T and a-T-menability from this point of view, so affine actions on Banach spaces, is to tweak a little bit the linear part. So consider the so-called affine uniformly Lipschitz actions. So for isometric actions on Hilbert spaces, there is an old theorem of Maser and Ulam saying that they're always affine, in fact. So as soon as we ask for isometric actions on Hilbert spaces, they're always affine. So they always have a linear part that is unitary and the translation part. But so if instead of that, we consider affine actions that are uniformly Lipschitz, that things change again. So that means we are going to look at affine actions where the linear part is a uniformly bounded representation. And well, as it turns out, high rank lattices have that property too. So even if instead of affine isometric actions, we consider affine uniformly Lipschitz actions, they will still have the fixed point property on all the LP spaces and actually on a lot of Banach spaces as well. So this is proved by Perelman Guillermo. And there is a conjecture of Shalom saying that, same as before, the hyperbolic groups will fail to have this property. Actually, they'll fail right at the beginning, so they'll fail for Hilbert spaces. So the conjecture is that every hyperbolic group will act properly on a Hilbert space as soon as we allow for affine uniformly Lipschitz instead of affine isometric. And there is also a weaker version, and that one is still open for pretty much everything. So if we're less greedy and we don't ask for proper actions, but we just ask for actions with unbounded orbits, so it will become every hyperbolic group has an action on a Hilbert space by affine uniformly by Lipschitz transformations with unbounded orbits. This one is also open. And there is only one case that is known, lattices of isometries of the quaternionic hyperbolic space. And this due to Nishikawa actually fixing pre-existing attempt of Julg. So this is how things are. So conjecturally, in this situation as well, the hyperbolic groups will stop having this property, but very little is known up to now. And now let me mention that other source of groups with this sort of oscillation between fixed points and a-T-menability, random groups. So up to now, I mainly mentioned linear groups and lattices, but another source are the random groups. And in particular, I only mentioned the triangular density model. And I wonder if I really, this slide contains a definition. Are you going to feel very vexed if I recall that definition, or should I just skip? Should I recall it? Okay, so you're not going to feel vexed. Good. So unfortunately, that nice description that I mentioned is never going to work. So all the theories of random groups are dealing with finitely presented groups because this is a countable class, and the finitely generated groups is an infinite uncountable class and beyond our reach. And of course, the nicest would be to find some exhaustion by finite subsets and do some probability on each of them and manage to say something. Unfortunately, this doesn't work like that. This model will depend on a parameter called the density. So one fixes a priori this parameter between 0 and 1. And this will actually encode how many relators we take by comparison to how many generators. So for every m integer, we consider a fixed set of generators with this cardinality. So all the groups we're going to consider are going to have that many generators. And then we consider only relators of length 3. And the number of relators of length 3 are essentially of cardinality, m cubed. And pretty much this one rather. And among all the relators of length 3 in this fixed set of generators, we choose randomly and uniformly a set of relations of this cardinality. So it is, if we consider all the possible relators, it is the power d of all the possible relators. And obviously cyclically reduced. And all the groups that are given by all the presentations chosen like that are the elements that compose this model. And one of the reasons why this model is really good, in particular, it's good for the kind of questions that I'm considering, is that it is closely connected with an older model of random graphs called the Erdős-Renyi model. And we are going to say that a certain property holds asymptotically almost surely if, when we increase the number of generators, the number of groups in this set, actually this should not be R, this should be D, sorry, D, satisfying property T, this probability increases to 1 when M goes to infinity. So this is what we call by a property being satisfied asymptotically almost surely. And for every D, and we have to consider all the Ds if we want to cover all the finitely presented groups. So yeah, basically we cut these countable sets into into countable subsets, each for each D, one of them. And here are a few results that would tell you what the choice of the density should be. If the density is larger than a half, the group is with probability. So I'm talking about properties that hold asymptotically almost surely. The group is either trivial or Z2. So this is Gromov. Actually, the entire theory was as far as I know, introduced by Gromov. But if the density is smaller than a half, then the group is infinite hyperbolic. So that means that we should work in this case. And in terms of property T, it's a theorem of Zook and further, I mean, like with more detail and improvements brought later by two brothers, Kotowski and Kotowski. If the density is at least a third, then the group has property T, asymptotically almost surely. And the reason for that is that in the corresponding graph model, random groups are expanders with a very good lower bound of on the first eigenvalue. Now, if we go below this threshold in the triangular model, the change is radical. The group is actually a free group, so a-T-menable. And this is due to Antoniu Kluczak and Świadkowski. And for d equal to a half, actually, both can happen depending on whether one puts a log at the denominator or the numerator. So that means that actually the threshold in this case is the third for property T. So below property T, there's nothing to discuss. And above, below 1/3, there's nothing to discuss. Above 1/3, we have property T. And so going to the first strengthening of property T that I mentioned, the one that was considering actions on LP spaces, and the requirement was that an affine isometric action on an LP space has to have the fixed point. And I've argued that the larger P, the stronger the property. Here's what we can say for random groups in the triangular density model. If we place ourselves in the same situation of a fixed density between a third and a half, so by the previous, we know that the group is infinite hyperbolic by Gromov, and we know that all the groups asymptotically almost surely have the property T. And what we proved with John McKay and later it was improved by Tim Dalat and de la Salle, we proved the following thing. The group, a random group, will have the fixed point property for all the LP spaces in an entire interval. And the interval is going to increase logarithmically in the number of generators. And interestingly, it will increase also comparably with the conformal dimension of the boundary. So the group will have the fixed point property on this whole interval, and the upper side of the interval has is at most the conformal dimension of the boundary. Actually, this follows from the result of you and Marc Bourdon, but there's also a lower bound. So f of g will be at least a square root of the conformal dimension of the boundary, and this was recently improved to linear. So Isar Oppenheim proved that actually here we can put a constant times the logarithm, and therefore a constant times the conformal dimension of the boundary. So that means that for random groups, if you consider these two sets of properties, so one of them actually purely metric, the conformal dimension of the boundary, and the other one related to actions on LP spaces, and we look at range of intervals where the group has the fixed point, the two are like comparable. They are related by linear inequalities, which is striking, and therefore like invites for the following questions. So let's consider a group that is hyperbolic and has property T. And let's consider the whole range of fixed point properties of this group. So of course, this is the interesting case, because if you consider a group that is A-T-menable, this is empty. So we want that this would be non-empty. So by the previous, it will contain at least the interval 1, 2. And since the group is hyperbolic, we know that this will have to stop somewhere, because at some point it will start acting properly on an LP space. Now, adapting the argument of Fisher-Margulis, we proved with Misha that this is always an open set. It's an actually ultra-limit result. And actually, this would be a time to pause and say that John McKay is one of the students of Bruce Kleiner, because besides proving a lot of beautiful theorems, he also launched in the world a lot of amazing PhD students. And it was great collaborating with one of them, and we still do. So a first question is, would this set always be an interval? So since we're talking about openness, it should look like that. And well, another natural question is the extremity of this interval in any way related to a geometric feature of the group as suggested here. So for instance, the conformal dimension of the boundary. And well, recently, Michael de la Salle and Amin El-Maragchi actually proved a result that clarifies situation a lot. So they proved, and in fact, they proved for topological groups, the following thing, that we can connect fine isometric actions on LP spaces and LQ spaces if P is smaller than 2. So if we have P at most Q, for every isometric action on an LP space, we can find an isometric action on an LQ space such that the co-cycles are related in this manner. So powers of the co-cycles are equal, which means that if this action is proper, then this action will be proper. And opposite, if we know that the group has a fixed point property for LQ, then it will have the fixed point property for LP. So that basically makes the picture much nicer. So it's, as I said before, that means that if a group has the fixed point property for LP, then it has the fixed point property below. And well, I mean, I did say that there is a version for 0, but if you want, you can just ignore it and imagine that I've put 1 here. And in the opposite way, if the group is A FLP amenable for a certain P, so if it has a proper action on an LP, then it has a proper action for all the P larger. So fixed point properties are going to be satisfied all the way below, and proper actions are going to be done to occur all the way above, which means that now we're talking about 2 intervals. And let me define those 2 intervals. So for one of them, I'm going to consider the supremum of all the P's for which the group has a fixed point property. And by the theorem of de la Salle and Maragchi, this range of fixed point properties is going to be described by an interval of this form, open. And if we look at proper actions, then, well, first of all, we know, of course, that the infimum for which we have proper actions must go below the conformal dimension of the boundary for hyperbolic groups. And the actual set of parameters for which we have proper actions, well, is going to be an interval. The thing that is still not clear is if the interval is open or closed. So that's the only thing we can say. And as far as I can tell, this is still not known. Which means that we can again ask a number of questions. So the first one is, well, obviously, first the group has fixed point properties until this extremity, with the extremity excluded because it's open, and then at some point it starts having proper actions. A first natural question is, when is the inequality an equality? Because again, let me remind you, for random groups, we have a linear inequality between these things. So there is a linear inequality between FP and between fixed point maximum and proper minimum both ways. And another again natural question is, can any of these two parameters be connected to some geometric feature of the hyperbolic group? And yes, in particular, this is it, the conformal dimension of the boundary again. Can it be related, either this or this, can they be related to the conformal dimension of the boundary by a formula? That would be really lucky, or at least by a double inequality. Now, as far as the fixed point property is concerned, this cannot be done. And we argued in a result with Ashot Minassian and Michael de la Salle, we can construct hyperbolic groups which stop having the fixed point property at 10, while the proper actions and therefore the conformal dimension of the boundary are as large as possible. So that means that there's going to be a gap between the fixed point property maximum and the proper action minimum as large as we want. And it also shows that at least this parameter cannot be connected to the conformal dimension of the boundary in any reasonable way. And the way we do this is that we use the usual small cancellation techniques to construct hyperbolic monsters. So some of these techniques also enter the Gromov monsters constructions. So for given any finitely presented group P and every group H, we're just able to construct a hyperbolic group with property T, which has P as a quotient and H as a subgroup. So for instance, if we choose P to be a lattice of isometries of the quaternionic plane, so that means that that quotient will start acting properly on L10. So that means that the group G, the hyperbolic group G, will also start acting properly, will stop having the fixed point property at 10. And then we consider a subgroup H, a hyperbolic subgroup, which has a large range of fixed point properties. So that will mean that the big group containing this one will not be able to act properly below N. But there is still the evidence coming from random groups. So random groups do have a connection. So that means, and of course, I mean, this kind of construction is highly non-generic. It's like a really, really twisted, non-natural construction. So that means that sort of there's a large class of hyperbolic groups for which one still can hope to find such an inequality, because like random groups are, and maybe it can be characterized in some sort of geometric way with some conditions. And then, of course, there's still the hope of relating the infimum of proper actions to the conformal dimension of the boundary. And now let me sort of mention briefly an attempt at a definition of spectrum. So now we have this situation. Let's say we take a hyperbolic group with property T. And so we know that it has a range of fixed point properties, but it also starts acting on some Banach spaces. And we want to test how strong, how robust the property T is. So that parameter f of G was actually measuring that. How robust, how strong is the fixed point property of that group? But of course, we restrict it in that case only to LP spaces, and LP spaces have a lot of limitations. Like for instance, subspaces of LP spaces are not LP, quotients are not LP, so it's a bit annoying as a class. So ideally, sort of the spectrum that would really measure the strength of the property T of the group would be to consider all the Banach spaces for which the group has the bounded orbit property. Now, of course, the first problem is that this is not a set, but since we are reducing to countable groups, that means that we can restrict to separable Banach spaces, and this is a set. So that means we could consider for a countable group, let's say a finitely generated group, all the separable Banach spaces for which the group has a fixed point property. And this one can be endowed with a topology. So Michael de la Salle defined the topology for that. And for topological reasons, it would be good to consider all the Banach spaces for which the group has the bounded orbit properties, also closed with respect to taking subspaces and ultralimits. So this is if we want to get a set that is reasonable with respect to this topology, so not too crazy. And I've added a third condition, which is closure with respect to L2 finite sums. And the reason for that is that for some Banach spaces, the fixed point property might simply come from the fact that the group has a very small, the space has a very small group of isometries. So it's sort of an artificial reason why we have the fixed point property. But then this sort of group, like L2 from a measure space to X, has a geometry very similar to X, but this one has a much larger group of isometries. So it's sort of natural to ask also to that we can also add L2 finite sums. And yeah. So for this kind of things. Okay, well, actually, maybe let me go down a little bit. Yes, this is it. Right. So yeah, I mean, I'm basically going backwards. I'm taking the largest class of Banach spaces possible. I'm trying to explain why we have to add a number of conditions. So this one is because otherwise topologically it looks really awful, and L2 because we don't want fixed point properties coming from this sort of not good conditions. And yeah, so let me first finish this, and I'll talk about the examples. And there's an old result of Hernandez saying that if we have a set of Banach spaces that is stable with respect to taking subspaces, ultramid, and L2 Dirac sums and duality, then it can be defined by a certain inequality. And this inequality is very similar to the uniformly curved condition of Pizier. So so that is sort of the largest reasonable class that one can consider are the uniformly convex spaces. So those for which we know that the balls are uniformly convex. And there is a subclass defined by Pizier, the so-called uniformly curved. And this class of uniformly curved basically covers all the known examples of constructions of uniformly convex spaces. So LP spaces, interpolations, quotients, subspaces, they're all in the uniformly curved. So in a way, the spaces that I consider cover all the uniformly convex spaces that you know. So it is still open an open question whether to construct a uniformly convex Banach space that is not uniformly curved. And so so this is essentially it. So I'm really considering all the Banach spaces that you can construct with reasonable means. That's it. So, the techniques that we considered: subspaces, quotients, interpolations, duality, anything. So they're all there. So that's essentially it. All the examples of uniformly convex spaces coming for all the classical constructions that you know are in here. Yes. Yes, this is also in the class. Yeah. All right. So anyway, so we do have a definition of the spectrum related to that. So the way we formulate this is via a definition, via a property called the Markov convexity. So we say that a Banach space is Markov convex if the following property is satisfied. Whenever we have a finite graph with a set of vertices gamma naught and the set of edges gamma 1, we endow it as usual with a stationary probability measure for the random walk. It's this one. And the condition for this space is the following: for the norm of the Markov operator on this graph is at most epsilon, so this should be gamma actually, then the norm of the Markov operator on this Hilbert space is also controlled. So let me explain a little bit what this means. So the Markov operator is the usual Lie Markov operator. So the Laplacian on the graphs is the identity minus the Markov operator. So if you have a spectral gap for the graph, that means that the Markov operator, the classical Markov operator, is contracting, and this is the thing that measures its contraction. And a space is Markov convex if, as soon as we know that for a certain graph the Markov operator is contracting, which again is equivalent in the language of the Laplacian, that we have a spectral gap of the Laplacian, then the Markov operator is also contracting for this kind of embedding on this kind of Hilbert space, and it is controlled. So the contraction is controlled by this function. Well, we work with functions that are square integrable and with expectation 0. I mean, it's the usual notation. And Markov convex means that this set, so when epsilon is small, this function is also getting smaller and smaller. So it's a way of saying that if we have a spectral gap, so if the Markov operator is contracting in the classical sense, then the Markov operator is contracting with respect to this space also in this sense. And here again, this includes the class of uniformly curved Banach spaces as defined by Pizier, which again includes the class of all the constructions of uniformly convex Banach spaces that you know. So they're all in here, and therefore they're all in here. So they're all Markov convex. The reason for us formulating it like that is it's sort of easier. And then, I mean, the definition of uniformly curved Banach spaces is even less transparent. So this one at least is basically saying that if I have a graph for which I sort of can control how well it embeds into a Hilbert space, then I can control how well it embeds into this. It's sort of geometric and visual. And so here is the definition of the fixed point spectrum of a group. So we're looking at spaces, at Banach spaces, for which this contraction of the Markov operator is controlled by this inequality. And so in this inequality, the constant C varies from 1 to infinity, and theta varies from 0 to 1. The Hilbert spaces correspond to C equal to 1 and theta equal to 1. And actually, this also covers affine uniformly Lipschitz actions on Hilbert spaces. So they are covered in the case theta equals to 1 and C in the entire interval. So actually, when we are considering this spectrum, we are also looking at affine uniformly bounded actions on Banach spaces. So for instance, the Hilbert space will be on the line theta equal to 1. That is the line. And so we are recording all the Markov convex spaces satisfying this inequality for which the group has the fixed point property. So they're all going to be recorded via these two parameters in a certain strip. And the set of Banach spaces thus defined is stable the way we want it. So it's stable by duality, is stable by taking quotients, by taking subspaces, I mean, for all the reasonable operations, L2 direct sums, ultralimits, and interpolation. So it's L1 is not in the set because due to, I mean, the very nature of this theory is sort of calibrated for uniformly convex things. So we don't want this to happen. So this is C and this is theta, and they're basically working in this interval, but we're basically removing L1. So as I said, the Hilbert spaces are here. The LP spaces are here because LP spaces correspond for P larger than 2, correspond to the constant 1 and theta 2 to the P. And then we also have the dual P less than 2, again, C equal to 1 and theta 2, 1 minus 1 over P. So actually for the LP spaces, we go once from 1 to 0 when we move from 2 to infinity, and 1 from 0 to 1 when we move below. And so we're looking at all the pairs of constants for which the group has a fixed point property in this strip. And it is open, same as before, same for LP spaces. It is, so if we have a certain point in the spectrum, then we have the entire rectangle in the spectrum, which in particular means that this set is going to be above the graph of a non-decreasing right continuous function. And so for instance, for a group G that is hyperbolic, this is going to look like this. So it's going to be above the graph of a function like this. So this I'm going to, somewhere here below, you have 2 over the conformal dimension of the boundary. And there is another thing that is sort of hidden in there and interesting, which is, does it intersect the upper line or not? Saying that this will stop here is equivalent to saying that the weak Shalom conjecture is true for that group. So if I say that the graph, that the spectrum looks like that for a certain group, basically I'm saying that the group has an action with affine uniformly Lipschitz transformations on a Hilbert space. So we don't know that. So the only group for which we know that is, the only groups are lattices of isometries of the quaternionic hyperbolic space. So this is essentially what we know. And actually the in the proof of the Latte and the LaSalle of their results of for random groups and the fixed point property they have, they basically prove that if we take all the hyperbolic groups and the union of all the spectra, this will cover the entire strip. And actually, not only it will cover the entire strips, but in fact, they will contain rectangles that will cover the entire strip. So just for hyperbolic groups, the strip is covered. And then what we can prove, that is what we believe is sort of the right spectrum that really encodes all the range of fixed point properties that a group can have. And then we have a result similar to the one that we had before, which is that, so if we consider an arbitrary finitely presented group, the condition that we have to ask is that this spectrum is contained in the spectrum of a non-elementary hyperbolic group, then its spectrum will actually be equal to the spectrum of non-elementary hyperbolic group. And the corollary of this is actually maybe more, poignant. If we know that a finitely presented group has a spectrum that is relatively compact, then we can find a hyperbolic group that has the exact same spectrum. So in the range of groups with compact spectrum, relatively compact spectrum, we can't find anything new in the class of finitely presented group beyond the hyperbolic groups. So it's this range that we have to consider. That being said, as I said, to begin with, the mere fact that all the hyperbolic groups would have a relatively compact spectrum is equivalent to the weak Shalom conjecture. And that is a tricky conjecture. And moving on to the last generalization of the fixed point property, the one in which we're just looking at actions that are affine, but not by isometries, but uniformly Lipschitz. Here are the results that we can prove. So this is again with John McKay. To begin with, a quite general condition. Every acylindrically hyperbolic group has an affine uniformly Lipschitz action on an L1 with unbounded orbits. And we can say little L1 or big L1. So it is some version of the weak Shalom conjecture, but it is not for Hilbert spaces, it is for L1. And unfortunately, so for isometric actions, one can move between L1 and L2. So having a proper action for L1 is equivalent to having a proper action for L2 and actually for LP. But it's not true if we are looking at this kind of actions, just affine uniformly Lipschitz. So that means sort of bad news is that we can only say it for L1. The good news is that it is for a large class of groups, because a cylindrically hyperbolic simply asks that the group has an action on a Gromov hyperbolic space that is acylindrical. And this covers a lot of classes, like hyperbolic groups themselves, mapping class groups that are not virtually abelian, groups of auto-orthomorphisms, free non-abelian groups, and just like a lot of groups have that. The second comment is that this is actually really the best that one can do because this class is really large. So it's true that it is not close to, it's not the Shalom conjecture because we have L1 instead of L2, but actually we can't have anything better because there is, so by combining results of Minassian and Dosin and Delat and De La Salle, one can construct an acylindrically hyperbolic group that has all the fixed point properties you can imagine. So if we move away from L1, if we look at LP spaces or even uniformly curved spaces or Markov convex spaces, so we can find an acylindrically hyperbolic group that has all the fixed point properties imaginable as soon as we make it act on a uniformly convex space, even by affine uniformly Lipschitz actions. So besides lattices, this is sort of the worst news you can have, or the best. It depends if you like fixed point properties or bounded orbits or the contrary. So that means that we can't put LP here because of this example. So we can't hope to have LP for P larger than 1. In particular, of course, we can't have L2. So this is the best that we can have because of this example. Now, if one goes to the smaller class of Gromov hyperbolic groups, what we can prove is, well, we have to restrict to residually finite hyperbolic groups. And there again, we don't really manage to have actions on Hilbert spaces. We only have actions on L1 spaces. But so within this class of residually finite hyperbolic groups, we show that every such group has an action by affine uniformly Lipschitz transformations on an L1 space. And moreover, the orbit is with the induced metric is quasi-isometric to the word metric. So the group sits really well in L1. And there is actually a Lie group version that we can deduce from here. Because of course, this one includes all the lattices in rank 1 of isometries in rank 1 symmetric spaces. And so, yes. It's because we use the Besvina, Bromberg, and Fujiwara construction of groups embedded equivariantly in products of quasi-trees. And using axes of pseudo-nosolves of, yeah, that is the reason. So as I said, because all the lattices are in here, we managed to prove the same for simple Lie groups of real rank 1. So for all these groups, we can find an action by, again, the same kind of action, affine uniformly Lipschitz on an L1, proper continuous and orbits undistorted. So again, all these groups are going to embed nicely into an L1 space. Now, of course, for one of the groups, this is no news, because this one is the group of isometries of the real hyperbolic space. So this one can be embedded like that even in a Hilbert space. So in this case, this is no news. But in this case, it is, because actually, for instance, one can show that there is no such thing for the group of isometries of the complex hyperbolic space if we're asking for isometric affine actions on L1. So this is, in a way, the best that is known for the group of isometries of the complex hyperbolic space already, not to mention, of course, that this is the group of isometries of the quaternionic space, so it has property T, and of the octonian plane, so it's even worse. So it's definitely worth mentioning. And I will now mention the last slide, the mapping class groups. So if you consider the mapping class groups of surfaces, we have the same property modulo 1 tweak. So if you consider the mapping class group of a surface of finite type, this one too admits an affine uniformly Lipschitz action on an L1 space or an L1 space. The only thing that we are not able to say, and we tried a lot, but we didn't manage, is that the embedding of the mapping class group via an orbit is a quasi-isometry. The only thing that we can say is that the lower bound for the distance distortion is not linear in the distance, it's linear in the distance divided by the logarithm of a distance. This is an iterated logarithm, so we can even iterate it, but nevertheless it's there. So for this group, we can't really show that the orbit is a quasi-isometric embedding. And of course, the main interest in this is that a lot of people are tackling the mapping class group with respect to various versions of property T and property T itself, and it's an epic struggle. And this shows that if we weaken the a-T-menability to consider uniformly Lipschitz actions affine on L1, then it is a-T-menable in this sense. And I should mention that a student of Michael de la Salle gave a construction, but not on L1 spaces. So the group does not act on an L1 space for hyperbolic groups and for the mapping class group. It is on a subspace. And well, so I mean, it's a very nice result, and the Vergara is a great and brilliant student. But of course, I have to explain what is the added values that we bring. See, his technique essentially is constructing a left invariant kernel of a certain type, while the construction we're giving essentially means constructing a cocycle, which is a proper cocycle, which is harder. And the distortion we have is also better because it's either linear for hyperbolic groups or almost linear for the mapping class groups. And Vergara's distortion is a square root of t. And which is where I'm going to stop. And sorry for annoying you with so many uniformly convex Banach spaces. I hope I did convince you, though, that they are to be considered for property T and a-T-menability.
Comments or questions?
So you might have said it, but is there an example of group that has the fixed point property on L1?
Fixed point property on L1?
Yeah.
Well, you're meaning affine uniformly Lipschitz action?
Yeah.
There is the hope of constructing an example, but for the moment, it's not, no.
Okay.
Can you give a general example of a construction of an affine uniformly Lipschitz action, which is not isometric?
So the way we do it is, I mean, one can always start by well, uniformly bounded representations that are not linear. So the way we do it is we're starting with quasi-cocycles for isometric representations. And we have a trick to twist this and to make it into a cocycle of a uniformly bounded representation. So it's usually, yeah, it allows some variation of the group. So okay, so let's say sort of the easiest way to do this is to have an isometric action on a space that is not, let's say, Hilbert itself, or it's not LP itself, or it's not uniformly convex itself, but has a renorming that is uniformly convex. So we do the renorming, and then the affine isometric action becomes an action affine still, but with uniformly bounded representation for the linear part. So this is where they appear the most often. And it's a natural thing to do because for a lot of classes of spaces, they are interesting in terms of the renorming. Like for instance, for superreflexive spaces, I mean, the best way to understand them is to say that they can be renormed such that they become uniformly convex. So this is where such actions appear. But I guess I'm guessing what is, yeah, I mean, it's in terms of a fixed point property, this is really much stronger for the same reason, because it says that the group will have the fixed point property no matter what the renorming is. And that's much better than the classical one.
Another quick comment or question? If not, let's thank the speaker again.
So I'm going to be talking about, is this too loud? Because is okay? Yeah. So I'll be talking about a very old question, which I'm going to describe it, and I'm going to state theorems about it. But this question has a dual, okay? Some way to phrase it is a dual, which is an easy fact, just like really just duality of linear programming. I knew it for decades, or 20 years, and everybody did. And everything I'm going to say, the main, the message I want to show is that even though we knew about this dual for a long time, it's worthwhile to force yourself sometimes to prove theorems in the dual, because then you discover things. So, but I'm going to start with the original formulation, which is classical. So this is, if you want a notation, terminology. So if you have a metric space, then you can associate a number to it, which is a bi-Lipschitz invariant. It's called the Lipschitz extension modulus. Of x, which is denoted E of x. And that's the infimum over, let's say, all the L, all the numbers. Usually it's going to be infinite, so something, usually there is no such L, such that, okay, so now for any subset, for every subset A of x, for every Banach space Z, for every one Lipschitz function F from the subset to the target space Z, there exists a function that is defined in all of x. There exists a function capital F that extends F, and has Lipschitz constant, and is a Lipschitz. Okay, so usually this number is infinite. There's, but when it's finite, it says something very strong. It says that here's x, take an arbitrary, however crazy this is x, this arbitrary subset A, however crazy, any target Banach space, any one Lipschitz function here. That's always a restriction of, let's say, if L is 100, of a 100 Lipschitz function, which is defined globally. When you have this, this is a workhorse in analysis. So statements of this fact, statements of this type are really useful. They appear as lemmas. It's very often that you have a partially defined function and you want, it's defined as a discrete subset and some net, but then you want to analyze it, you want to prove something, you want to compute, you want to use continuous methods, you want to use a Fourier transform, you want to differentiate it, you want to apply heat flow, but it's defined in a subset. So you want to extend it in some smooth way. And most of the applications, there are very sophisticated applications, but most of the applications that appear in the literature are somewhere in the middle of a proof. You have a function defined partially, you extend it. So this is a very useful thing when it's finite. It's generally infinite. So is the definition clear? Now, sometimes maybe two comments. First of all, the fact that I wanted the target space to be a Banach space is just traditional. I mean, we also, all of the theorems that I'm going to say are studied also when the target space is a cut-zero space or spaces with certain curvature bounds, etc. This is, I'm just doing the classical formulation of the question. And sometimes I will care about what this A is. So when I write EXA, it's the same thing, but I don't have the quantifier for every subset. So sometimes I care about a specific subset, like a separated net in X. We're going to discuss this. And then, so EXA is going to be the same thing. It's just the smallest L, such that every function from A into any Banach space, every one Lipschitz function can be extended into an L Lipschitz function. Okay, so that's the variant of this. And I want to discuss what is the dual question. So there must be, okay, the way I wrote this, it's a parameter of the space, E of X, but I used something external. I quantified, right? There is all these quantifications here. One of them, right? So I look at every subset, and there is every Banach space. But this is just a property of the metric space X. So there must be a way to, and I'll write it in a second. There must be a way to understand what this number is by looking only at X, not quantify over every target Banach space, and that's where the dual will come. But before doing that, I just want to tell you, just so we calibrate. So two things to calibrate is first, what are the kind of questions that people don't know, and what are the spaces that we're interested in? So these are not exhaustive. We don't know the answer. For example, when Rn with a Euclidean metric, what is the growth rate of this thing? And that's a major open problem. But let me just calibrate how big these things are. So the general question that I'm going to be interested in is evaluate, again, up to lower order factors, E of Rn with some norm. Okay. But again, this is I'm interested in many norms, but the questions that I'm going to ask are going to be open. They're open for they're open for all the norms. So maybe I should say so there's a theorem that I proved in 2021. Which says that E of L infinity n, so Rn with the L infinity norm, is bounded above and below by universal constant multiples of root of n. And prior to this theorem, there was no space for which we knew the asymptotics. And after this theorem, this is the only space for which we know the asymptotics. Okay, so in particular, what is, again, up to lower order factors, E of Rn or L to n. But any other LP space, we're not talking about exotic spaces, Rn with a Euclidean metric. And when we write a dual, you're going to see this is a very interesting question about the geometry of this room, for example. We're going to state this about a question in Euclidean geometry in a second. Okay, so this is the only space, L infinity. Okay. If you read this work, you can read the proof and cook up artificially spaces for which the proof gives asymptotics, but the only natural space for which we know the asymptotics. Of course, maybe even a little too much than what you want to know. There's a lot of work on these things. So let me, but again, maybe I should keep the definition. So just to calibrate, so here are the best known bounds in general. So again, X is Rn with some norm. Okay, then E of X is always at most n. This just means up to universal constant factors, and it's always at least n to the c, where c is a universal constant. The bound here is a major famous theorem of Johnson, Lindenstrauss, and Shechtman. From 1986. So, and still today, so an example of an open question is, can we improve this to little open? So that's they did this in 1986. We have new proofs of this, but we do not know to go below. And the lower bound here is from this paper from 2021 of mine. I don't want to talk about the paper. I want to show new things, but there is a big history here. It was for many years open if this is even going to infinity, if you can get any bound going to infinity for every x, in particular for Rn with Euclidean metric. The fact that this goes to infinity is something that I did in my dissertation back 22 years ago. So this is like one of the main questions that they ask in their paper is what can you get a lower bound even for Hilbert space? But in the end, it behaves like powers of n. So the game, okay, when I say the general question, evaluate up to lower order terms, it's always going to be what is the exponent. So I'm really interested in something like log E of x over the log of the dimension. I'm going to lose logarithms. I might even not mention them, but the invariant, the geometric invariant that I care about is the exponent. It's some power of n, and it's a universal, it's a constant independent of n. Okay, so for the answer is 1/2 for an infinity, and that's the only space we know. Yeah. There are 2, I don't 10, I don't know. I don't remember, like 1/20. I don't know, they're reasonable constants with whatever the proof gives. Actually, this is one of the progress I will mention today. I know a little improvement of the constant, but I do not know what is the best, don't know what's the best possible lower bound, what's the best possible upper bound, and even for Euclidean space. As I said, the only space for which we know the constant, which is 1/2, is L infinity. Okay, so and there are many, many, many bounds, and I will mention more as we go along. But just to keep in your head, the enemy here, or the goal, is what is the exponent of n. Okay, and that's where the geometry is hidden. Okay, so let's write the dual. Okay, so this is called Wasserstein rounding. And it's the following, I think, extremely natural question. It's what I'm going to say is just the same question. So it's, if you think that extending Lipschitz functions is natural, then what I'm going to say now is the equivalent. So remember, so we had our space X, could be our n, this room, for example, and we have the subset A of X. So let's say so X could be the room over here, and A is all of our I's, for example. Okay. So there is this ambient continuous space and maybe a discrete subset inside, but it's any subset. Now the goal of X, so you take a point, so here's X, and here A is in here. So the goal of the Wasserstein rounding problem is the following: every point in the ambient space X looks at the subset A, so I'm looking at all of your I's, and it wants to define a notion of what it means a random I, a random element of A. So for every X in X, let Ux be a probability measure on A, supported on A. Borel, all of the issues of measurability are taken care of in these papers. I'm going to ignore them. So so every point in this room looks at the subset A and says, I want to decide what it means to be a random point in the subset. Okay, so imagine the integer grid. It's rounding to integers, to a random integer. Now, you want to do it in such a way that there are some consistency requirements. So the first one, if X is already in the subset, then U of X is the delta mass at A. This is what corresponds to extending, right? And 2 is that for every 2 points, X and Y in X, the transportation cut distance, remind me, is at most L times their distance. So the Wasserstein 1 norm, or the Wasserstein 1 norm of a distance of a difference between probability measures. Does anybody here does not know what it is? you want to find a coupling of the two measures, ux and uy. So there's a way to assign a point in the support of a point in A to a point in Y, such that an average, you did not travel far. Does anybody, please, should I write down the definition of transportation cost, or I did not write the definition of Lipschitz constant, for example, but is that okay. So, yeah, so you look at the infimum. So you integrate over x times x, the distance from x to y, d pi xy, and you take the infimum over all pi, where pi, the requirement on pi is that its marginals are ux and uy. So if you look at f, the integral of f of x, d pi xy, d pi, sorry, what do I want to say? You want to give the talk? I think push forward. If I'm defining Wasserstein, I'm not going to use the push forward. Okay. So you want that if you you integrate f of x d mu, maybe x is a bad notation because we have the 2 points x and y. Sorry about that. That's what x and y are the point in the space, so let's call them a, b. Okay. Okay. So the integral of f of a d pi a b is the same as the integral of f of a d mu y of a, which is an x, and this is an, and then correspondingly the f of b is integral of x, f of b d mu x of b. So this is, I look at all the possible ways to do this. This is a way to find like to put a notion of a random pair such that the a coordinate is distributed according to ux, the b coordinate is distributed according to y. Okay, so you want to couple them, but you want if you take this random pair, then their expected distance is as small as possible. Okay, or we can discuss the push forward if you want, but okay. So those of you who know Kantorovich duality should not be surprised that this is related. This is a very easy exercise, except that so I want to say that the smallest L here is the same as the L in the Lipschitz extension problem, but that's not true. Okay, so first of all, when you have such a scheme, a rounding scheme, there is an obvious way to extend it, right? If you have a function f which is defined only on the subset, going into some Banach space, then you want to define capital of f of x to be the integral over a, right? So the measure ux is in the element is d mu x a, right? That's the obvious. Once there is when a point outside of a decides what it means to be a random point in a, and little f is defined on little a, then you could take the expectation of the value of f on the random point that corresponds to x. And it's little exercise that this definition is perfect for getting that this capital F is L Lipschitz. Now this is not quite the dual. Does anybody see what the issue is? No, the issue is that this capital F here, if I define it this, if I look at this rounding scheme, this capital F here always takes values in the closure of the convex hull of the values of little f. So if I do it like this, which is actually something that is studied, it's very natural. F goes from capital from this metric space not into Z but into the convex hull of f of a closure. But that's if the minute you take this is an average, okay? And it's known that there are examples of functions little f that have an extension when you go into the target space, but not into the convex hull. Not when you insist that you go into the convex hull. There are many proofs automatically give convex hull whenever you use duality or random methods, etc. But this is not the same question. This is what, let's denote econv, because that's a perfectly legitimate different by Lipschitz invariant, which I want to get to, which is, later. That's something surprising here. So econv is the same thing as the definition of the Lipschitz extension modulus, except that you may add this as a requirement, that you can extend every function from A going into a Banach space in such a way that you don't, the extension is not going into Z, but it's going into the convex hull of the image of little f. Is this nuance clear? So in order to get the real dual, one, exactly. So this is what I'm going to write. So that's Wasserstein rounding, and what you really do. I shouldn't have erased this. Okay. So you do the same thing, but you allow signs precisely. So now you take a, so for every x in x, you let mu x be a measure supported in A, with total mass 0, with mu x of A is 0. So this is the same as saying as mu x plus of A. It has a positive part is equal to mu x minus of A. Okay. And so that's one. And then sorry, and the consistency. So first of all, so you want mu x. So if x is in A, x happens to be in A, then before we wanted mu x to be a delta mass at A, but that of course doesn't have total mass 0. So let's just fix any A0. It's going to be independent of the choice of base point. Okay. So fix it, and two, the same thing. So now you can look at mu x minus mu y. What's written here? So this is for every 2 points. Before it was a difference of 2 probability measures. Now it's a difference, obviously, of 2 positive measures, but with the same total mass. Because the total mass of mu x, each of these has a total mass 0, so everything has total mass 0. So the total mass of mu x minus mu y plus and mu x minus mu y minus is the same. So it makes sense to couple them. The definition, I didn't need the probability measures. This condition just means that they have the same total mass. So this does make sense. And this is the same thing. So the smallest L in this version of the problem is the same L as in the Lipschitz extension problem modulo completion. So you need to actually, there is something called the free space. You need to, the space of all sign measures with total mass 0 has a natural, you look at its completion in the Wasserstein 1 norm, and we actually, in the proofs, we have to deal with these objects which did not have to be measures, but forget about it for now. This is, when we write the proofs, think about measures. So the smallest L here is E of x, and the smallest L in the previous version, in the probabilistic version, is E conv of x. Is it all clear? And then, and the proof of this is very easy. Okay, this is a known and old, and there's nothing new happening here. So, so this is something that we knew for a long time, and the question is, how can we use this to get bounds? And somehow, so from the new results are with the new results that I'm going to mention are joined with Mark Braverman. And we have a whole paper where we really investigate the dual, and by forcing ourselves to think about the dual, we succeeded to solve, I counted this morning, 7 quite old open problems, and I'm gonna show them to you. And I'm sure this is not exhaustive. So when you figure out how to prove something in the dual, then you can start thinking about all the problems you know, and some of them become easier in the dual. Okay, but just one thing I want to clarify. So the duality is a very easy thing. So all this, when I'm going to start stating theorems that we proved, I'm going to show you one of them, at least one of them, how I think about the dual. But in all of these cases, I don't need to think about the dual. Okay, so because the duality is easy, I can hide the fact that I discovered the proof in the dual and write it as extensions of Lipschitz functions. So when you will read the paper, you don't have to think about the dual. But I would be lying. But we discovered all of these things because of the dual. Okay, but you don't really need it. So everything can be written just about Lipschitz function. I won't do that because I think that would be misinformation. Okay, but so everything I'm going to say we found out by thinking about the dual. Okay, so one of the things. So here's an example of a theorem that I might give a hint of how we prove it, but this is a theorem that I have to admit I was shocked by. I really I have papers, old papers in which I conjecture the negation of it. Okay, E of x. This comes from lots of equivalences and examining within the proof, and maybe as we see, we'll start doing equivalences. You're going to see where it's coming from. But E of x is finite if and only if E conv. So actually, this rounding problem, probability measures and general measures with total mass 0, just if you care qualitatively, it's the same question. And so, as I said, there are examples of functions f going from a subset into some Banach space that are one Lipschitz. There is no Lipschitz extension, simply no Lipschitz extension to a function which is defined, and takes values in the closed convex hull of f. But there is a Lipschitz extension going into the target space. So these things that seems like a contradiction, except remember the quantifiers. For specific functions, this is not true. But if you require something to hold for all functions, then it becomes the same question. You understand that this is it seems so. I can give you examples of functions where I cannot go into the convex hull, but if I want this to be finite, I need to prove a theorem for every possible function, not just look at one function which is not extendable. Okay, so this is one of the corollaries of looking at the dual, which it's not the main one I want. Let me tell you what I want. So, and you can do all kinds of computations. So I want to. So separated nets are an especially important case. So there is the case when. So if you want a notation. So many of the applications of Lipschitz extension, I would say the majority, we care about the case when the subset A is an epsilon net in the superspace. So it's very often that you do something discretely, you will have some discrete approximation of the metric space, and you want to extend it to the whole space. I think that definitely in our thing, that's the only case that we ever looked at. So let's just give it a name, because this is an especially important case. So E net of x is just the same thing, same definition, but you restrict it. A runs over, not over all subsets, but over all possible epsilon nets of x for every epsilon. You can do also epsilon delta net. So all discrete sets which are every point is close up to epsilon to one of them, and every 2 points are epsilon apart. And you can do 2 parameters. But let's just have a little less parameters. So you understand what the notation of E net is? This is the same thing, but instead of rounding to your eyes, I'm rounding to a net in this room. And this, when you have a continuous object and you try to round to a net, this seems, for a long time, I thought that maybe this is the worst possible. Okay. So So again, by looking at the dual, and this is, I want to explain later where this comes from after I say some results. So I'll explain a little bit the proof of this. E net of Rn. So this was open. We didn't know this for Rn with the Euclidean norm. Now I know it. It's bounded above and below by universal constant multiples of 4th root of n. So this is one of, we see this in the dual, and I'll explain. So if you look at Rn, you take an epsilon at in Rn, you have every, this is really classic rounding. You have every point in the continuous space has to choose a probability measure above supported on the net. That, but I should say that then it's the same as econv in this case. So in this case, it doesn't matter. So you want to define a notion of a random net point, then you can do it in this Lipschitz way. You can do it while losing only 4th root of n, and you cannot do any better. Okay, so the fact that you cannot do any better, that was an old theorem. This is so the fact that E net L2n is at least 4th root of n. This is Mendel and myself. I don't know, 2010, something like that. The key, the very creative idea behind this is a beautiful theorem of Carlton, which, when you understand what's happening, it gives this. So the main point that I'm going to show you afterwards is how to round into a net and lose only 4th root of n. Even this is a Euclidean question. It's a net in Euclidean space, and the answer is 4th root of n. This is not no exotic geometries or anything. And I wrote L2n, but I probably won't remember. But for any space that you can imagine, I can compute this. Okay, so all the LPNs, I know the answer, etc. Okay, so maybe in particular. So also E net of L infinity n, which turns out also to be 4th root of n. Okay, this is what it turns out, and I'll explain where that is coming from. So in particular, because I told you of the theorem that the original E, the extension from an arbitrary subset was root of n, that was the 2021 theorem. In particular, we get that E net of L infinity n is not equivalent. So not up to there are different orders of magnitude. So this idea of rounding to a discrete to a separated net being the hardest thing from a continuous object to a net, that's not true. This is one of the things that I was wondering about for a long time, and now I can prove this is the only example I know where they're different. And LPs, I told you I can compute things for LP spaces as well. But for L2, I still don't know. So conceivably, E of L2n is 4th root of n. So I mean, I do not know if for Euclidean space the best thing, the hardest set to round to or to extend from is a net. So there is a chance that for Hilbert space, for Rn Euclidean space, we can solve. Well, I don't think I'm close, but maybe it's 4th root of n. So here is another one that comes from analyzing a dual. It's technically more complicated. It's less important than the net, but it just seems like a very classical question that should have been studied in number theory. I ask number theorists if anybody. So what happens when you try to extend from the integer grid? So this is a very natural question. You have a function, a one Lipschitz function defined on the integer grid, and you want to extend it to a Lipschitz function defined on all of Rn. What is the smallest Lipschitz constant that you can do it? So the answer is, again, by looking at the dual, bounded above and below by n to the 1/6. And again, for all the LP spaces, we know the answer. It's some formula which is written, but I never remember. It's some function of P which, right, z to the n is a one net in L infinity n, but not in L2n, right? So for L infinity n, the answer is going to be n to the quarter because of what I wrote here. The net can be z to the n. That's a one net. but there is more interesting geometry, and the proof here uses the product structure. So there are things that can be, I mean, eventually maybe a student can look at what happens for general lattices, what is happening. But this strange, so this is a very clean question. You really want to round, it seems like some simultaneous Diophantine approximation. You have a point in Rn. You want to choose a notion of a random integer. So each of you choose a random integer point in such a way that you're consistent. That if you happen to be an integer point, you choose yourself. And 2 points which are near each other, you can find a matching between these integer points that on average didn't move much. How much do they have to move? The answer is n to the 1/6 and not any better. And that's the same as the extension problem. Yes, no, so I will explain what the measures are in the net, where the fourth root is coming from, and then for Z2 then is much more complicated. So, but I think it's better to start with the simpler. That's my goal. How much time do we have? Does anybody know? Good. So I'll explain what they are after I show the simpler one. Okay. Okay. So how much? Okay. Okay. So I want to say okay, so there's another invariant of a metric space which hides behind this behind a lot of what's happening here, and that's called the separation modulus. So so this is again a bi-Lipschitz invariant that you can assign to every metric space, and it has been studied. This one has been invented by the computer science community because this is, you will see when I explain it, it's an obvious clustering problem. So this is the inf over all sigma, such that okay, I wrote over Rn. When there is scale invariance, I don't need to introduce a scale, but for a general metric space, I need to introduce a scale. So such that for every delta bigger than 0, there exists a distribution over random partitions P, but P is a random variable. I'll draw a picture in a second of X into pieces or parts of diameter at most delta, such that for every 2 points X, Y in the space, I look at the probability that X and Y fall into different partitions, different atoms, into different atoms. P. This probability is at most sigma, the parameter that I'm looking for, times the distance between X and Y, and I make it scale invariant. So in a norm space, you can take delta equals 1. So suppose I want to partition this room into pieces of diameter at most 1, such that any 2 points are never near the boundary. If they're very, very close, then they fall into the same piece. So that's of course nonsense. Okay. But what happens if you allow randomness? You want to partition in this room into tiles of diameter at most 1, such that any 2 points, if they're very, very, very close to each other, then with huge probability, they'll fall into the same tile. It will be a rare event that they fall into different tiles. And it's going to be rarer and rarer as they become closer. Is that clear? So it's a way to chop up a metric space You have a metric space, for example, Rn. You want to chop it up into pieces of diameter. Each one of them is diameter at most delta, so they're small. Yet any 2 points, x and y, if they're very nearby, this happens very rarely. Again, I need to divide by delta to make the scale invariant. In Rn, I would just write pieces of diameter 1, or in a norm space. But in general, this is so it's the notion of a separation. So in the smallest sigma, call it sep. So this was defined by Bartali in 1996, and it is a very important thing in algorithms. It's a useful way to simplify things. You cannot chop the floor into tiles of diameter 1 such that all points that are nearby are in the same tile. But if you, for example, look at the tiles below you, but if you shift them randomly, then this is a pretty good encoding of the floor that you're sitting on by a discrete object. Okay, is this clear? Or so so back in 2003. Lee and myself proved that E of x is always less than sep of x up to a constant. Maybe the constant is 2. So if you can simplify randomly a metric space in this way, then you can extend Lipschitz functions. And that's a specific construction coming from well, the definition of separating partition. One of the corollaries, so this is of looking at the dual, and this is something that, again, I'm personally shocked. I didn't expect it, is that E of x is finite for every metric space if and only if sep of x is finite. So actually, this random simplification is the only way to extend functions or to round. And it's so this is at most that and at least square root. Okay, so that's what we really, okay, and this comes from looking, so this random partition that we did, this comes from Calderon-Zygmunt theory, when the intuition is coming from harmonic analysis, is actually the only way to extend functions, qualitatively. There is, quantitatively there's a difference, but one is fine. So a space admits a random partition of this type, a random simplification, if and only if you can extend it. You can extend Lipschitz functions. Okay, so this is something that I still am surprised that somehow this captures it. So now I can tell you so for a rich, I'll tell you in a second, class of norms on Rn, and it's not just rich, it's all the norms we care about, all the LP spaces, all the I care about using these things for spaces of matrices with natural Schatten norms or operator norms, etc. This rich class includes all of those. So there's a certain rich class which I call canonically positioned norms, but it includes all the spaces you're thinking about, the classical ones. Okay, so for a rich class of norms on Rn, x, E net of x is up to universal constant, up to lower order terms. So here there are logarithms hiding. But we care about the exponent. So this is, so E net is actually square root of sep. Now, why am I saying this? Okay, so in particular, the reason I'm saying this is that because this is in 2021. In this paper, I dedicated a lot of effort to devising methods to compute sep of x, and there is a formula for sep of x. So for this rich class of norms, which I can define it, but think about Hilbert space, LP, etc. And for a rich class of norms, there is a formula I compute there I gave there is a formula. For step of x, again, up to lower order terms, up to logarithms, okay? So I actually know how to compute step of x, and therefore I can, extensions from nets, is solved, okay, as far as I'm concerned. There are exotic norms for which I do not know how to answer, but I'm quite sure that if you hand me a norm, I'll be able to compute the answer. But for in general, I can tell you what it is. So there's notion of a volume ratio. The volume ratio of a norm, so you x is a norm, volume ratio, which I didn't, VR of x. This is an invariant which is used all over the place. Okay, it is the following: you draw the unit ball. So it is hexagon. B of x is the unit ball. Okay, you look for the John ellipsoid, the ellipsoid of maximal volume contained. Epsilon is the ellipsoid of maximal volume contained in the unit ball. It's uniquely defined. This is what Fritz John proved. And then you look at how much volume, much did the volume increase? So I said it in words. I didn't write because I want to get to some proofs. Okay, so you look, given a norm, this is a bi-Lipschitz invariant of it. Okay, obviously a linear invariant, but it's also a bi-Lipschitz invariant. You look at the unit ball, it's some convex set in Rn. It contains, look at all the ellipsoids which are contained in it. One of them has maximal volume. And you ask how much, you look at the nth root of the ratio of the volume of the ball to the volume of epsilon, to the volume of this maximum volume ellipsoid. And then the theorem is that step of x, this clustering problem, is again up. When I say this, I'm lying a little bit. There are logarithms. Okay, it's not up to constants. Step of x is the volume ratio of x star times root n. Now, volume ratios, computations of volumes are really simple. Okay, so this is very, very easy to compute. So you can do crazy things. I wrote one of them just to show you what can be done. Which one? What? It implies that if this is finite, then this is finite. That's my. I intended to say that the lower bound that we got here, then I added this afterwards. You're right. It's very, yeah. This was very confusing. The converse is what we get here. Okay. So just to show you the kind of computations we know how to do for the separation problem, and that involves all kinds of things in Banach space theory and isoperimetry and reversing the isoperimetric inequality. There are a lot of nice geometric questions that remain open, but for this big class of norms, these are norms for which there are isometry group X irreducibly on Rn. By the way, that's the connection between my talk today and my talk last week, but the only overlap is you and the organizers, right? But the way groups, isometry groups act on Rn is what's hiding behind this. So for example, just to indicate the kind of things we can do, and now thanks to the formula up there, we can compute the extent. We can simply solve extension from nets for essentially anything. So now look at all the n by n matrices. So it's an n square dimensional space, and the norm is just to take the operator norm from LPn to LQn. Yeah, you have a matrix. You think of it as an operator from LP to LQ. It is an operator norm. So you have volumes to compute, and it turns out that this is what you get: n to the 3/2 minus 1 over the minimum of P and Q, if P and Q are at least 2, if it's n to 1/2 1 over the max, if P and Q are less than 2, if P and Q straddle 2, but in this way, So Q is between P and Q, but P is the smaller. Then you get N. And if it's the other way around, which is the only thing that remains, you get another phase transition. You get N to the bigger of 1 and 1 over Q minus 1 over P plus a half. You see, I don't remember it myself. But these are things, so this clustering problem, this nonlinear clustering problem, we can really compute it. And the answers are interesting. So now if you want to look at all the matrices with operator norms, with LP and Q, and you want to, this is a perfectly nice norm, not an exotic one. And you want to extend from an epsilon net in it, collection of matrices, something defined in an epsilon, and a one net, right? It's scale invariant. Then you have to take square root of this number, and that's the answer. Upper and lower bounds. Thanks to the fact that E net is the square root of the SEP, and the SEP is something that I worked on earlier to compute. Okay, so there is progress, but I still don't know the main original question is what is E of L to N, for example. But qualitatively, we know that all the methods that we used before, extending into the convex hull, random partitions, are actually qualitatively, in terms of finiteness, these are the same notions. And qualitatively, they hit the mark with the square root phenomenon for nets, when you have only one scale relevant. And so there's some solution of a quite old question of Bourgain. I'll stop. I want to say an example of what these measures look like. How much time do I have? Perfect. Okay, so let's do the net. So E net of L to N, I said, was bounded. So I told you the lower bound was this thing that was done before. So I want to prove this. Okay. Okay. And then as I do it, you're going to see what you're going to get a hint of what happens for other norms as well. But let's do Euclidean geometry. So this is really just a purely Euclidean question. This is not some question about Banach spaces or anything of this type. Okay, we have an epsilon net in this room, but high dimensional version of it. And you want to round the point from the continuous space into the discrete space. So let's call N, let's N in our N is a one net. The metric is the L2 metric. Okay, everything is scale invariant. So let's assume it's a one net. And for every X in our N, let's just notation, phi of X be a point, fix any, if there is multiple, I don't care. Fix any phi of X in N such that the distance from X to N is the distance from X to phi of X. It's the nearest point. Okay, so here's X. It's actually going to be simple, but there is a surprise, I think, but which is kind of obvious after I say it. Okay, but the hindsight is 2020. So here's X, and here is phi of X, distance at most 1. And so, okay, then I remember X. The goal of X is to find the probability distribution over points in the net. Okay, so your first guess would be just assign the delta mass of phi of X, but that will clearly be discontinuous. You cannot do that. So I want to somehow smooth these things out. So let's so I need let psi be the function which I just need a smooth version of the distance to X, to the net. So let's say this is a quarter. This is 1, and just go from 1 down to a quarter and then 0. This is like the cutoff function. Okay, so that's psi. And let's define lambda of X to be psi of the distance from X to the net. No, I think the norm of I already defined. Okay, this is I need I really think about the distance from X to the net, but I need to smooth it out for what I'm going to write. Okay. And And what I'm going to do is I'm going to do the following. So this is a number between 0 and 1. So I'm going to flip a coin that has probability heads lambda, probability tails 1 minus lambda x. And so I'll define mu of x. So mu of x is going to be lambda, yes. So it's going to be lambda x times the delta mass at the nearest point. So right, so this is already done, right? If you're at the nearest point, it's lambda x is 1. Okay, so you're going to be, if you happen to be in the net, you're at the net. But the surprising thing is, maybe not surprising, maybe obvious to you. By now it's obvious to me too. If the coin becomes tails, then I'm going to do something crazy, which is so let me draw the picture. I shouldn't have erased it. X, phi of x. We know that this here is at most 1, right? So what I'm going to do is I'm going to draw a huge Euclidean ball around x of radius r. I'll optimize over r. R is a parameter of the problem. So when x is far from the net, there is a little ambiguity. Where should x go? Because there are other nearby points. So I'm actually going to go crazy, and I'm going to say I'm going to use this ambiguity. I'm going to take a uniform point in the ball around x of radius r, Euclidean ball, and so I'm going to take a uniformly random point in this huge ball, and then I'm going to move to the nearest point of that point. So here's your push forward. Okay, so understand, if x is very close to the net, I'm going to say, okay, then I want to go to the nearest point with high probability. But there's going to be a small probability which becomes bigger and bigger as x is further from the net, where I have more and more uncertainty, and then I'm going to use high dimensionality. So we're going to see what happens in high dimensions. These huge balls, if x and y are near each other, overlap a lot. So there is actually a very good coupling if they're far apart. Okay, so when x is too far from the net, I'm going to just go boom, far away, and then to the nearest point in the net. And a version of this is what's going on in Z2DN, except it's more complicated because there's a product structure, and we use the product structure, and all kinds of rounding to integers, etc. So there, but the idea, and this is what comes in a lot of these things, is that we realize is that that when you're not sure what to do, exploit high dimensions, and when you feel good about what your nearest point, then actually go to it. And the versions of this with all kinds of technical complications is what gives a lot of these sharp results. Okay, so but let's do the computation, what happens here, and see what R should be. This is the uniform measure. So again, so say, think of lambda of x as you flip a coin. If probability of head is lambda x. So lambda x is 1 when you're, or tending to 1 when you're very, very close to your nearest net, to the net. Okay? You flip the coin, you got a number. With that probability, you go to the delta mass at the nearest net point. Okay? If it became tails, then you say, okay, you know what? Let's draw a ball. I didn't tell you what R is. Let's take a uniform, according to the volume measure, a uniform point in this ball of radius R, and take the nearest net point to that point. Okay, at that point, like I give up. Okay. Now, of course, I don't want to give up too much, because so there's an optimal, there's a tension here, and this tension, there is an optimal R which gives 4th root. So let's very quickly do the computation. Right, so Rn is geodesic, so I want to check. So I already got the delta mass at. If x is already in the net point, then it's a delta mass. So I want to understand what is mu x minus mu y Wasserstein 1. Right, that's the game. So and I want to show that this is at most something times the distance from x to y. That's I'm reminding you what, and the smallest L I can put here is the rounding, the answer to the rounding problem. Okay, so this is a Lipschitz condition between two. This is what's written here is a Lipschitz condition between the map for the map that assigns x to mu of x, going into Wasserstein 1. Okay, so I can assume that x and y are as close as I want, because if you prove Lipschitz condition for small distances, then it's also true for big distances. It's a geodesic metric space. So as I'm going to do the computation, I will think of x and y as very, very, very close, much closer than the one of the net. So without those, let's say the distance from x, let's order it. So the distance from x to the net is at most the distance from y to the net. This is without loss of generality. And I want the distance from x to y to be small. I think, let's say a quarter. I think it's going to be enough. Smaller than smaller than the epsilon, which is 1 of the epsilon net. And let's deal with the interesting cases, which is when the distance from x to the net is also less than a quarter, or maybe 1/40. I'll see in a second. Okay, so this is the harder case when x is close to the net. Okay, you'll see what to do if not. Okay, so here's x, here's phi of x, and because x is so close to phi of x, listen, remember the net points are 1 apart, so factor 4 longer than the distance that you see here. Okay, so this force, because the distance from x to y, I'm using metric convexity, is less than a quarter. This means that phi of x is phi of y, and it's a triangle. Phi of y cannot be bigger because the distance between phi of x and phi of y is 1. This is less than a quarter, and this is less than a quarter. It's a triangle inequality. Okay, so this is where I'm using that we're talking about the net. Okay, so phi of x is phi of y, and then then we know exactly that mu x minus mu y is lambda x minus lambda y times the delta mass at phi of, I wrote this down, delta mass. These are the things that you don't do on the board. Delta mass at phi of x minus phi sharp, uniform measure of the ball around y of radius r, plus 1 minus lambda x. And then the difference which we care about between these uniform distributions. U is uniform. R is still a parameter that I need to choose. Okay, so just subtract. Okay, there is the difference, the mass, the delta mass of phi of x, the difference between them is the lambdas. This is a Lipschitz function. So okay, so now I want to compute the Wasserstein 1 norm. It's a metric space, so I can compute the Wasserstein 1 norm of this distance plus that. And now let's do them separately. That's going to be the tension between that will force me to choose my R. So the first term, because lambda is a Lipschitz function, psi was this one Lipschitz cutoff function, is you have, that's lambda x minus lambda y is at most dxy. That was a Lipschitz function. How much does it cost you to transport? That's a trivial transportation problem. A uniform measure to a point. It's the radius of the ball plus the distance between the centers. A measure to a point is easy to. That's not a hard transportation, of course. So, so this is r. I guess +1 or something. I'm going to maybe do some constants. So if there wasn't the push forward here, then it would mean how do you transport a uniform point on the ball to x? You have to just map every point here. You have no choice to that. And the distance between x and phi of x is at most 1. That's it. And that's it. Right. Is that clear? And there's a 20 or 1 or 4. Now, what happens to the uniform measure? So this is if everything is scale invariant here. So let's think of the case r equals 1 for a second. So you have x, y is very, very, very close to x. Here's the ball around x, and this is hard to draw. The ball around y. So if x and y are very close, they overlap a lot. So when I want to transport these uniform measures, forget about the push forward for a second. Because the distance between x and phi of x is at most 1, it always gives me an additive 1 because of the. So I'll keep all the optimal transformation. I'll keep all of these in shape, and then I'll map. I mean, I can shift a point here by the vector y minus x to a point y. So what's really remaining is the volume of these little shells divided, it's uniform, divided by the volume of one of these balls, times the distance between x and y. That was when the radius was 1. And when the radius is r, it's the same as doing the same thing for x minus y over r. So what you get is that you get the area, the volume of these shells, which is a little computation, but it becomes root n over r. Root n is what the ratio between the volumes of these shells to the volume of the ball. This is just a computation, very easy computation, polar coordinates. And then x minus y, this is scale invariant over r. Okay, so there you go. You know what r to choose. The best r is 4th root of n, then you get the 4th root of n. And versions of this much more complicated because there is more structure that you need to exploit, is what gives n to the 1 over 6 and z to the n and things of this type. But you see, when you think about rounding, there is this game of you're happy when you're near a point, and when you're far from a point, what's helping you is amenability, if you want, like boundaries are small, and there's a lot of isoperimetric questions behind these computations, etc. Okay, so I'll stop here. They're not the bad A for L infinity, or for any LP bigger than 2, for example. But for L2, I don't know. I simply don't know. For L infinity, what is the bad A? Okay. So, I mean, I know the bad A because I'm in a computer. So the worst A for L infinity, I know it. It is, here is it. So L infinity contains inside it a subspace, a linear subspace through the origin of dimension n over 100 or some proportional to n. And this subspace has the property that any projection onto it has norm of order root n. Okay, so you have to prove that. It's a nice fact, but it's classical from the 40s or something. So you can cook up a subspace of proportional dimension such that if you try to do a linear projection from all of our n onto the subspace, then you pay a root n. Okay. Now, if it weren't a projection, if it were a retraction, and we say the Lipschitz constant of a retraction is at least root n, then extending the identity mapping is the same as retracting. So I can take this subspace, this can be our z, and also our a, and I can look at the identity mapping on the subspace. I want to extend it to all of L infinity n, but I'm extending the identity mapping. It means I'm retracting in a Lipschitz way. The Lipschitz constant is like the norm of a projection. But this is something that already Linden shows it in the 60s. It's a nice argument. There's a rigidity theorem saying that the best way to retract in a subspace is using a linear mapping. So that's how you. So this is the opposite of a net. It's something really, really organized that does it. But this is exactly what I cannot use in Hilbert space. This is why there is still a chance that a net is the worst possible. In Hilbert space, there is always a projection. So there's this. So this doesn't work for a Hilbert space, but it shows that it's for some natural spaces, the answers are different.
All right. Now, down to mathematics. All right. So I have put some of my co-authors' names on the board. I will mention them as they are relevant, hopefully. So G in the stock is going to be a simple Lie group, and you really won't lose anything if you think almost all the time that G is the isometry group of the hyperbolic space, which, I being me can't not write in Lie group notation, but you don't have to worry about that. And it's even, not being me on this occasion, the cases of SL2R and SL2C are of probably most interest in a sense I will try and make clear as we go along. So this is not higher rank or even higher dimensional. You know, some of the most interesting questions are about surfaces. And we're going to have gamma sitting in G, a discrete group. And I need one definition, which is that if I take, let's just go here, G in G commensurates gamma. If G gamma, G inverse intersected with gamma has finite index in both gamma and this conjugate. Perhaps the naive way of thinking about this is, you know, you might ask for an element to normalize some subgroup, and we're not asking for normalization on the nose, we're asking on normalization up to some sort of finite missing. It's almost normalizing the subgroup. And, you know, it's easy to check that I'll start using the letter delta for it. If I look at the commensurator in G of gamma, so all elements that commensurate G, commensurate gamma, sorry. This is a subgroup. And very funny. I didn't notice. I'm about to write something on the board that I find very pretentious, but I didn't notice at the time that I suggested it to my collaborators at where I'll say a little bit more about the name in a minute. I'm going to call something the Greenberg-Shalom hypothesis. And when I suggested to my collaborators we call it this, I really was not thinking about Riemann at all, which is the only other thing I know of in mathematics that's called a hypothesis. But I'll tell you more about why it gets this name in a minute. And it was first proposed by Greenberg in 1975 for exactly isometries of hyperbolic spaces. And then Shalom sort of reproposed it in around 2010 for more general G. And it says that if delta, so this commensurator group is dense in G, then gamma in G is a lattice. And I guess maybe we have such a broad audience here because Bruce has such a broad interest, I should say that just means that the volume of this quotient is finite. And if you want to think about it as meaning this quotient is compact, that, you know, it's a fine lie to live with for the hour. And I should say, you know, the caveat that I would forget is, you know, gamma not the trivial group, or if you're not thinking about a center free group or finite. Yeah, there are some small caveats. Yeah, they both suggested this, and part of why I call it a hypothesis is if you either read Greenberg, who really wrote about this in 1975, he really comes very close to making this a conjecture, but he's just gets a little gun shy. You know, he's like, oh, it's probably true, and maybe even this or that, but he gets a little gun shy of making it a conjecture. And Shalom also, when he asked it, it was also just kind of clear. I was actually talking in Pisa to Yehuda about this question last week because he was at last week's conference, and you know, he didn't know what to call it. He's like, it's my speculation. He almost said conjecture even over coffee. So you know, people seem to believe this. And the other reason why I call it a hypothesis is there actually has been a lot of attempts by various people to computer test it that I might remember to mention later. Not exactly in this form, but in related forms. There are computer tests that have been running, run on things that this question is essentially equivalent to. And so before I proceed, since really we are all geometers here, and that looks like algebra, I just want to tell you that the slogan about commensurators is hidden symmetries, and tell you why and what that means for the people who don't know. You know, this really is geometry. It looks like algebra, but it's really geometry. So if I take an element of this commensurator. How to get this right with quantifiers. Then there exist two covers, M prime and double prime. Oh, I forgot something. So let M be, let's just say, HN mod gamma. You know, same explanation works for other symmetric spaces, but let's just stick to HN because this is just an informal description of what this means geometrically. Then there exist these two that are finite covers of M. Such that delta gives rise to an isometry between them. You know, delta is an isometry of the universal cover. There's no reason to believe that delta is a map at all of M. In fact, it is not. But there's some pair of finite covers where delta gives you an isometry from one to the other. And that's, you know, the geometric meaning of this, and it's really why anyone studied this notion in the first place, I believe. And, you know, what does delta dense mean? It then implies that if I pick any x and y in M and any epsilon greater than 0, then there exists some covers M prime and M double prime and an isometry from M prime to M double primes realized by some choice of delta, such that delta of x, well, delta of any lift of x lies within epsilon of your chosen lift of y. So you can pick any lift of x and then map it by some isometry to within epsilon of any lift of y you pick. And if you think about this even for a few minutes, geometrically, it feels like this, well, that just can't ever happen. That just seems like it shouldn't happen geometrically. And there is a reason why these things got studied anyway, even though geometrically it feels like they can't happen, because they do happen. And this is, you know, it's often called the theorem of Borel's, but in his paper, this much is just a proposition. And I won't define all the words except by examples. So if gamma is an arithmetic lattice, and if you don't know what one is, you should just think of gamma being, you take your group, you look at its integer points. All of your groups will always be matrix groups. It always makes sense to look at your integer points. Arithmetic lattice is a very slight generalization of that. Then delta is in fact dense. And the reason why, which is actually an exercise in any reasonable special case, is that delta contains the rational matrices in your matrix group. And, you know, I'm telling a few lies in general here, but, you know, this is an observation in a paper of Borel's where he actually proves other things and, in fact, computes in essentially all examples what exactly delta is. It contains this group at finite index in general, but Borel actually, you know, what he's doing is not proving this thing, which is really an observation that you can prove for yourself in the next hour if you don't want to listen to me. But it's he's proving something else. You know, especially if you just do this for, you know, I guess I should write down even the more special case, SL2Z and SL2Q. That one is really that pair of groups is a very easy exercise to check. And, you know, the intuition that I at least have here is that this should be something deep coming from number theory that lets you make Borel's thing, even though it's trivial work. And there's a partial result in that direction that very much inspired at least Shalom's thinking about this, which is a theorem of Margulis that says if gamma in G is a lattice and delta is dense, then gamma is arithmetic. And Margulis proved this. This was about 1960. This was 1975. No, 1974. I'm going to be right. So he basically says that the examples arising from Borel's proposition are the only things that can happen if you're assuming your manifold is compact or finite volume. And it's a funny story. After thinking about this for a while, I asked Margulis if he'd heard of Greenberg. If you read Greenberg, it's fairly clear he had not heard of Margulis and did not know that this theorem had been proven a year earlier than his paper was written. He does, in fact, in the paper speculate that maybe it's not just a lattice, but maybe it could actually be that it was only true for arithmetic lattices. He literally says that in the text, not knowing that Margulis proved that if it was a lattice, it was arithmetic a year previously. And Margulis had not, also not heard of Greenberg or his thoughts about this when he proved it, when he proved that. Yeah, could almost fit the known results about this thing on what's left of the board here, but I won't push my luck. So, other partial results on, what I will now actually write as GSH, which, once you write that in your notes, you realize you're making a reference that you didn't want to be writing, but okay. It's not the Riemann hypothesis, but the main point of the talk is not going to actually be the partial results, but the many things that this being true would imply. Again, it's not the Riemann hypothesis. They're not that important, but they are interesting and important, I think. So this is known first if gamma in SL2R is finitely generated. And that actually Greenberg proved. And later I'll tell you how if I have time. So that's in 74 or 75. And then life gets harder if you just do SL2C. And again, finitely generated. This is MJ and I guess it's 2011, building on earlier work of Leininger, Long, and Reed. The final case is definitely Mahan's, but there was an earlier paper by them in the same year that he definitely used. And so, I'll just say that this, this is, we know a lot about Kleinian groups these days. This is throwing the kitchen sink at the problem. So it really is, there's no chance that anything like this kind of argument will extend to larger Lie groups, not even to SO41. There's no chance you can use anything like the argument there. The other thing I will say is that finitely generated here is a bad assumption. We all, I grew up as a geometric group theory like a large part of this audience, and you normally think, oh, groups should be finitely generated because that's, what's natural. You all already know that normal subgroups shouldn't necessarily be finitely generated. You take a finitely generated group, you take a normal subgroup of it. Normally it's finitely normally generated, not finitely generated. And commensurated is even weaker than normal. So they're in all the natural applications, finitely generated is not guaranteed. And then the other thing that's known, there are two results in the case where gamma, where let's say lambda in G is a lattice. And the gamma that we're caring about in the Greenberg-Shalom hypothesis should be a normal subgroup of lattice. This, why is this interesting? It's another sort of error, right? The error that we all make when we first learn algebra is that a normal subgroup of a normal subgroup should be a normal subgroup. It's not. But you might also make the error that a normal subgroup of a commensurated group might be commensurated. It's still not. But Shalom actually, what really got me interested in this question is basically a conversation on a beach in Tel Aviv with Yehuda Shalom in 2019. He asked this version, what about normal subgroups of lattices? And two results in sequence. If the Betty number of lambda mod gamma is positive, then this was settled by Coberta and MJ literally before Yehuda asked me the question personally. Van Limbeek and I proved some special cases of this before finding out that they had done it. right afterwards in the summer of 19, but they had done it earlier in 19. And then just, in general, this is a recent preprint by myself, MJ, and Van Limbeek. And I will say that this proof is differential geometric, in keeping with sort of the theme of relationships between fields of the conference. That theme was very differential geometric. The general case, we can't do that way. This proof is very much about looking at what happens to differential forms that come from this first Betti number. And the other remark I'm supposed to make right now, shall make here, is that even 3 number 1 is false for gamma in the automorphism group of a deregular tree, and this is due to Berger-Moses in 96. Berger and Moses didn't know they were disproving a case of Greenberg-Shalom in 96 because they didn't know about it. But this is just some sort of warning that this is not just, many things about lattices and Lie groups turn out to be true for lattices and automorphism groups of trees. Discrete groups similarly. This is a warning sign that there's something more going on here, that you can't just extend to automorphism groups of trees, and it was actually known quite a while ago. Oh wait, do I want to do that? No, I want to erase the hypothesis and start telling you some implications of the hypothesis. Okay. Yeah, no, the main point of the talk is to advertise the hypothesis, to see if any of the ideas from any of these many fields that are coming together here can make progress on this hypothesis, and to see if something can be made of the connections between these fields. Maybe make progress on this conjecture. The first thing is the first surprising application is the following. If a group, and here I don't know which kind of letter to use, a group, it's either discrete or continuous or whatever, G is called coherent. And this is a definition that I believe, all I know about this comes from early work on the question due to Serre, and I think the definition is even due to Serre, but I'm not sure. If any finitely generated subgroup what am I supposed to call it by? Is finitely presented. I'm going to try and remember to use letter D, delta, for groups that turn out to be the commensurator in Greenberg-Shalom when one proves the application, and gamma for the ones that turn out to be gamma in the conjecture, but I might forget sometimes. But it is intentional when as long as I remember to do it. And the theorem that now is by Brody, myself, Mahan, and Van Limbeek, which henceforth will be BFML. And this should be out on the archive soon, but isn't quite done yet. So I won't put a date on it, is that this Greenberg-Shalom hypothesis implies that SL2Q is coherent. And the famous question asked by Serre is whether SL3Z is coherent. That's a really famous question asked by Serre that a lot of people really like. This is asked in the same, this is a question of Serre. It's asked, I think it's a few lines away in the same paper. Serre asks about not just SL3Z, but SL2Q and SL3Q. Those are the groups he seems to care about. And if you don't like rational points and you want discrete groups instead, this of course implies the same thing for SL2 of Z adjoining 1 over P, which is a famous example of what's called an S-arithmetic lattice, and it is true that Sarah actually also asks explicitly about this example. And as long as I keep the 2 and don't make it a 3, it follows fairly easily from Greenberg and Shalom, modulo one thing I haven't explained yet. So it's almost an exercise to think of why this thing I call our theorem is true. I'm not going to claim that any of the implication. For this, I need GSH for G being SL2R. Oh, and this I should admit too. Thank you for asking about Assaf. You remind me. And I need it for SL2QP for all P. And I need it, not for arbitrary subgroups of these two groups, but for subgroups that come inside the rational points. So you need not quite the full force, and you need it just for these groups. And so really SL2, most of the applications that are interesting you can get just from thinking about SL2. And this is certainly an example of that. So I do want to tell you about something slightly more technical that that's just an application I like. That's sort of one of the places where I first started thinking about related things that at the time I did not know were related things. And I will eventually get to a question that I believe I've asked, about 200 mathematicians, probably including at least 15 people in this room. But we'll get there when we get there. I certainly think I asked Bruce this question at some point. Okay, let's think about what else we can do with this. And for this, I do need a slightly technical definition, which is, and I'll do it in the case where it's applicable. So if I think of gamma sitting in SL2R or SL2C, just some subgroup, and I don't even need that it's discrete for this definition, there's a field, it's called the invariant trace field of gamma. And in this setting, what you look at are the traces, these are matrices, so you can take their traces, you look at the trace of G squared running over G and G. And you look at the field, the field that generates. And in fact, the fact that this is an invariant of the conjugacy class of this is a conjugacy invariant of the group is a theorem of my now colleague Alan Reed's. So this is it's a conjugacy invariant. That's due to Reed. I'm afraid I forgot to look up when. And the thing that one can prove that is of some interest in the three-manifold community is the following two things. One is that if M is a compact hyperbolic manifold, and therefore just by generally known stuff, the fundamental group lives in SL2C, then what GSH tells you is that there exists, and it's really lots of in senses one can make precise, but I don't want to, gamma in gamma with the trace of gamma an algebraic integer. And I just want to say that, why would you ask for such a thing? So if you live in my world, which many of you don't, there's a hierarchy of Lie groups. And for the biggest Lie groups, biggest simple Lie groups, we know all their lattices are arithmetic. And being arithmetic will imply that any sort of trace invariant of any matrix in your group is an integer, or at least an algebraic integer. If you want to just think integer, there's a technicality that you shouldn't worry about. And it's even a recent theorem that's proven in a surprising way that that's even true this integrality is even true if you look at complex hyperbolic manifolds. It's a recent theorem of Esnault and Grushonig that's proved using some of really amazing stuff about the Langlands program by Laurent Laforgue. And it's just, you sort of wonder, well, does any of that sort of arithmeticity survive if you look at just three manifolds? And we know very well that it doesn't, but something is left, which is a little bit surprising. I should say that it's the fact that this thing is always an algebraic number is definitely not my theorem, and is ancient, and you should look in the book by McLaughlin and Reed if you want to see a proof of why it's always algebraic. The fact that it's an algebraic integer, if GSH holds, is what we've observed. And the thing that's, I think, even more surprising is if you take, this group should be delta, just because I said I was going to make delta the groups that are the commensurator in Greenberg-Shalom, and that's what that group is. I think maybe I'm confused. Yes, it's delta in Greenberg-Shalom. So if you take delta to just be the fundamental group of a genus G surface, and you assume that you have some realization of delta inside SL2 Q bar, and I won't say much about this, but there really are a lot of such realizations of surface groups that live inside the algebraic integers entirely. Then you get the same thing. You get a similar implication. And maybe here's where I should just mention verbally some of the computational work that's been done on this problem, is that there are such surface groups written down explicitly by Long and Reed, and then Thiemann variations, Brody has written down many more of them. And first Long and Reed, and then Agel, and then Brody have thrown these things into computers and computed balls of absurdly large radius, trying to find these integral traces, and not found any of them. A number of people have tried to prove the theorem those computations lead you to believe, including with the assistance of computers, but it has failed so far. So, you might think from this intuition, from the hyperbolic, certainly the guys who think about arithmetic of 3 and 2 manifolds would have lent the other way on this problem, until I told them that this thing about commensurators implied the opposite of the answer that they want, and I've convinced Reed and not Agel to change his mind. So, it's now become a question of some controversy whether or not this is true. And I should also say that, asking these kinds of questions about these groups are folklore questions that go back to the 90s. And what's new here is the fact that they have something to do with commensurators. Are there any questions? This says that I have this thing, and the Greenberg-Shalom thing implies that, lots of gamma and delta have integral traces. And we'll get in a minute to the version of this that I know I've asked Vlad before, which is this: you can think of this as having something to do with surface groups or three manifold groups acting on products of trees. And, the integral traces are essentially fixed points. Integral traces correspond to fixed points for certain actions on trees. You would naturally expect not to have fixed points. And I will get there in a moment. But first, I want to ask sort of a more general version of the question that I'm going to ask about trees, which is a question that when I first realized it was a question, I thought that was absurd and it couldn't possibly be an open question, but that's about 4 years ago, and it's still an open question now to the best of my knowledge. Let's take 2, G1 and G2, simple. And it's important for the connections to things real or p-adic Lie groups. And the question is, if I take delta in the product such that delta projects to a dense subgroup of G1 and G2. Question is delta what's called an irreducible lattice? Which, anyone who has any, intuition coming from geometric group theory should probably think that question is absurd. But that is all the known examples. We'll call such a group an irreducible subgroup. Because it lives discretely in the product and can't live discretely in a factor. The fact that I'm saying this with 2 and not k factors is just me keeping the exposition relatively simple. There are versions with more factors. Oh, did I forget to say the delta? Yes, I did. Thank you. Yes, it's discrete in the product and indiscrete in the projections. And in this context, I said dense in the projections. You could say indiscrete and Zariski dense, and it's the same thing. There are a bunch of equivalent things you could say that different people like to say. I mean, I've avoided the words Zariski dense so far on purpose because I feel they're not kind to a more geometric audience. But some statements and proofs and things simplify in that case. So, a special case of this question is, are there irreducible copies of the free group or a surface group? And you can pick your G1 and G2. It's not known. The question asked this way, I'd sort of been thinking about on and off for surface groups of acting on products of trees where G1 and G2 were both p-adic and it was a surface group. I've been thinking about that on and off. And I was at Alessandro Iozzi's birthday conference in Zurich and having lunch with Nicolas Monod, Pierre-Emmanuel Capras, and Yves Benoit. And I'd asked Nicolas the question the day before about surface groups acting on products of trees. And I'd asked Pierre-Emmanuel Capras the question at least 3 times before. And suddenly Yves Benoit asked the 2 of us whether we know the answer, the 3 of us, whether we know the answer to this question. The 3 of us start laughing because we assume that Yves is just taking the piss out of me because I've asked so many people this question. But he'd come to it on his own and asked it. And he was the one who pointed out to me that, I don't need these groups to be p-adic. I don't need these, the group to be a surface group. It could be a free group, could be a surface group. They can be 2 copies of SL2R. And, what you get for free when you take a surface group in a product of trees is the density of the projections. That follows easily from older work of Serre. So, this is very open. And I will say that in this case, when Yves asked us this question, he very clearly thought the answer was yes, these irreducible subgroups should exist. And then one should find them and study their moduli. It turns out that that's not so easy. How am I doing for time? Okay, we're doing it right. So the proposition that really is a proposition that I will prove for you because it's easy. Well, modulo 1 thing that's also easy, but that I won't prove for you because it's something I already used in my thesis. And so I think of it as ancient history, even though it's not as well known as it should be. So what's the proposition say? Let me get this right. I don't know why I'm calling this one a proposition and the other one's theorems. They're all just fairly easy consequences of thinking the right way about these problems. This Greenberg-Shalom hypothesis implies yes for the question, provided one of G1 and G2 is p-adic. And it really should be at least one. It works if they're both p-adic. And this is really sort of the glue that connects the Greenberg-Shalom hypothesis to both the questions I've told you so far and a whole bunch of other questions that I don't have time to tell you all the strange applications and implications this hypothesis has if one can prove it. But I hope I'm at least motivating that it's kind of interesting. And I just want to sketch the proof because it's kind of easy. And it sort of tells you why commensurators are interesting. And we're just going to do the proof in the case that, say, I said one of them should be p-adic, so we'll let G2 be SL2 of QP. And you'll see that I'm not really using anything about the choice of SL2 or the fact that that's QP and not a finite extension of QP if you know those things. And if you don't, it's probably more informative to stay simple. So the main fact one wants to use is that SL2 of the p-adic integers in the p-adic numbers is a maximal compact open subgroup. And that's not too hard to prove. It's a standard fact, and I won't prove it for you. And then I'll give you the proof from that fact as a sequence really of exercises and then one use of some other fact that's harder than this one. This one is really quite easy, but I don't want to get lost in basic things. So exercise 1, which really is the definition of the words compact and open and maximal, is that SL2 QP commensurates SL2 ZP. You might say, hey, wait, those aren't discrete groups. You seem to be defining commensurate for discrete groups, but all I said was finite index. Finite index makes sense. So that's an exercise that's easy from the definitions of open and compact. Once you believe me that this thing is the biggest compact open subgroup. Second exercise, which is purely algebra and is really a trivialization, is that this implies, and let's be careful, let's call it pi2 of delta. This is, we have pi2 from G1 cross G2 to G2. We have pi1 from G1 cross G2 to G1. Maybe you would have guessed what those letters means if I didn't define them, but I'll define them. This implies that pi2 of delta intersected with SL2 of ZP is commensurated by pi2 of delta. The exercise I forgot and I left out is that these projections have trivial kernel. That's another exercise. That's exercise 0. It's got the same sort of proof as everything else here. And then what do you do with this fact? You take this group, pi2 of delta intersected with this maximal compact. Exercise 3 is the following. Take pi2 of delta intersected with SL2 of ZP. I want to really think of that as living in the product, take pi2 inverse of that. And then really I want to push it into the first factor. So I'm really taking pi1 of that, call that thing gamma. It's just this commensurated subgroup. This is commensurated as an algebraic property. So pushing around by these homomorphisms changes nothing about commensurated, but this group is discrete in G1. This too is nothing other than an exercise in the definition of compactness. Probably I'm saying these things too fast for anyone to actually do the exercises, but these are really the steps. And if you were to take a photo of this board and go home and try to do the exercises, a large percentage of you would succeed. You won't promise people who just study Ricci flow that this will come naturally, but it's actually not hard. And probably if you've taught undergrad algebra and topology, you could probably still do it. It would just take you a little longer than it would take people who know this kind of thing. And it's discrete in G1 and commensurated by phi1 of delta, which is dense. And therefore, Greenberg-Shalom hypothesis implies gamma in G1 is a lattice. So out of doing nothing but quoting you this Greenberg-Shalom hypothesis about things, I've found at least a lattice somewhere, but I promised you a lattice in the product. And then the fact is that it's a proposition. He actually proves something stronger, which is harder, but this version is just a proposition due to Venkataramana, that somewhere around 2000, no, it must be earlier than that, somewhere in the 90s, that gamma a lattice implies delta a lattice. Once you've found a lattice somewhere, you're kind of done. This is what Venkataramana tells you. Yeah, it just tells you that, if I'm looking at a product and I have something that's a discrete group that's already a lattice in one factor, if it's bigger, it has nowhere to go but to be a lattice in the whole product. It's a very algebraic fact, but it's one that we need here. So where am I for time now that I've actually proved something? Yeah, so that really proves that this Greenberg-Shalom hypothesis implies this fact about irreducible subgroups being irreducible lattices, at least when one factor is a product. I guess one thing that I'll just remark verbally is, you might think, well, that's really weird, because now you've got a really weird difference between SL2R times SL2R and SL2R times SL2QP. And depending on your background, you either believe such things are plausible or you think that's ridiculous. And I will just say I have friends with varying background who believe both of those statements. If you wanted to run the same proof with 2 copies of SL2R, you run into trouble with this, compact open subgroup business that I said at the beginning. There is a language of approximate subgroups that you can use to generalize this Greenberg-Shalom thing to a statement about irreducible subgroups and their or irreducible approximate groups and their commensurators, so that this argument goes through. There really is a way to do that. It's a little bit tricky, but the asymmetry may not be real. It may just be an artifact of the fact that we like groups and commensurators better than we like approximate groups and approximate commensurators. And I certainly don't want to get into those technicalities here. I did promise I would mention this thing about trees, which is I don't know if I should say for many years it was my favorite question, but it was for many years the question I asked every mathematician I had coffee with, because almost every mathematician could think about it. Again, doesn't work for people who work hardcore in PDEs, but for anyone in geometric group theory, geometric analysis, geometric topology, it worked. Started a lot of interesting conversations. A lot of people had a lot of interesting ideas. I still don't know the answer to the question, so I'll just advertise it again. So this is, we're going to take T1 and T2, bounded valence trees, and ask, the question is, let's take sigma G, closed surface of genus G. And then question is, can I send delta, that in this case will be pi1 of sigma G, into aught T1 times aught T2. And I guess I'll just say, I want a proper homomorphism. Saying proper for a homomorphism is a little bit silly. It's just a homomorphism with discrete image, but this is a question. It's been a question that where I learned this question was from being at a semester at MSRI in 2015. And I was working on something related to these arithmetic properties I told you the Greenberg-Shalom hypothesis would tell you about three manifolds and surfaces. With some collaborators, we were trying to prove similar things, but only about high-dimensional hyperbolic manifolds. And I realized that every proof we came up with would prove something about surfaces, and it would, in fact, give me an obstruction to having such a homomorphism. And I just assumed that every geometric topologist worth their salt could hand me such a homomorphism. And so, since I was standing in MSRI and Ian Agel is an old friend and he was down the hall, I just went and asked Ian because I assumed he could give it to me in 17 seconds. And I got a sequence of emails from Ian over the next few days as he tried to build an example of this. And eventually I got an email from Ian that said, yeah, I can't do that. And I have since, I once jokingly said I've asked 100 people this question. I don't know that that's wrong. I certainly have asked a lot of people this question. No one's answered it so far. It doesn't mean that one of you won't answer it, by breakfast tomorrow. Yes. I have no idea at this point on this one. Couple remarks. One is Greenberg, this GSH, I've been sticking to GSH, is relevant if, let's call this thing rho of delta lives inside a product of p-adic groups. Otherwise, it's really not relevant. I already told you that Greenberg-Shalom is wrong just for an automorphism group of a tree. But the other question is also wrong for an automorphism group of a tree. There exist irreducible subgroups. Now this is remark. Maybe that's one. Remark two is there exist irreducible subgroups of aught T1 times T2 that are not lattices. There are lots of different constructions of this, but there's some interesting constructions of this, I believe, coming out soon that I'll just, got to get authors in order and not put the authors in the name and the order name of the author who told me about it, followed by their co-author. There's a paper that is, I believe, in progress of being generated by Jingjin Wang, who's Bruce's student, and Mahan MJ, who's my collaborator, producing particularly nice examples of irreducible subgroups of this product. So like that question is wrong for trees. The commensurator question is wrong for trees, but I still don't know if there are surface groups in this product. And I find that very annoying. I don't have any, I will say I kind of believe this Greenberg-Shalom hypothesis. If I didn't believe it, I wouldn't give you an hour-long talk about the things it implies. This one, I don't know. I've never quite known what I believe. It's asked explicitly in a paper I wrote with Spotzer and Stover and Larson, but I think it's much older than that. Question? Okay. Okay. I want to tell you two things at the end. How much time do I have? What? Oh, 10 more minutes. And I can tell you both things. So let me tell you two remarks about why when Zhangdong asked me what my talk was about, he jokingly said dynamics, right? And so far it looks sort of like a little bit of geometry and mostly algebra. But there is a dynamical motivation for a dynamical way of thinking about this problem that I think should in some sense work. But again, I've tried fairly hard and not succeeded. And maybe I shouldn't tell it to you because you should find a different approach and make that succeed instead. But I'll tell you what I've thought about just for honesty. So, in this case where M is just H2 mod gamma, in this case, ergodicity of the geodesic flow on the unit tangent bundle of M implies at least that there are no free or surface irreducible subgroups of SL2R times really, want to be careful. Yeah, you pick your p-adic group, I don't care. That implication I know how to prove. Why would I suggest ergodicity of a geodesic flow? Well, ergodicity is about there not existing any invariant sets. And somehow, the commensurator isn't actually symmetries of the problem, but it's almost symmetries of the problem. And so having invariant sets while having commensurators seems like a very hard thing to arrange. And there are various ways in which you can try and make that precise. And then the even stronger implication is if G has property T, then ergodicity of the analogous action, so of the A action on G mod gamma, where A is the Cartan subgroup. And I think I'm close enough to the end of the talk that I won't tell you what A is for those who don't know. It's the maximal diagonalizable subgroup. And this thing is sometimes, in some cases, in the rank 1 cases, this is some kind of frame flow. In the higher rank cases, this is often called the Weil chamber flow. It's, it's just, if you don't know what A is, it's just some sort of generalization of the geodesic flow on a surface that makes sense in all these contexts. This implies the Greenberg-Shalom hypothesis, and so all the consequences of it for G, a group with property T. So in particular, because I need G to be SL2R or SL2C for many of my applications, it doesn't get me my applications, even if I could prove this. It would be evidence that this idea is not wildly unreasonable. The only sort of evidence you have that's solid for these ergodicity statements is that it is true that the limit set of gamma is the entire boundary. And I will assume that a large number of you know what that means if I'm in a hyperbolic space, and so not say what it means in general. This is true in hyperbolic space. This was observed by Greenberg, and it was generalized to, general by Mahan. In fact, this fact about limit sets, which is like a 2-line triviality, is how Greenberg proves the result about finitely generated groups acting on H2, because it's long since known that a finitely generated group of isometries of a real hyperbolic space has full limit set if and only if it's lattice. That's an exercise 2. Again, maybe only for those who know some geometric topology or geometric group theory, but and full limit set and ergodicity are in some sense vaguely related. They're nicely related under special conditions. Regrettably, the special conditions are not interesting for these questions. And I'll tell you one more thing this all implies, which I will not refer to as a question or conjecture, but a chestnut, because this thing is very old. The first place I found it in writing is in a paper by Linden and Ullman in 1969. It was recently promoted to being a conjecture by Kim and Koberta in about 2020. It's also in the, what's it called? The Kurova notebooks, these old questions about groups. It's in there. It's really an old question. You take the following 2 matrices. Oh, I did this backwards from the way I normally do it. Let's see if I can get it right. Let gamma be the group generated by gamma S be the group generated by A and BS. Should I be calling that gamma S? Be calling that delta S. Sorry, I want to keep my consistent notation choice. And the conjecture by Kim and Koberta that was last by many other people earlier as a question, is that if S is rational and in the interval from -4 to 4, then delta S is not free. Sort of a strange question when you ask it this way. The thing you're supposed to notice is that if I take a generic, this is sitting in SL2R. If I take a generic pair of non-commuting unipotents in SL2R, I can conjugate, so this is one of them, and the other one has this form where S might not be rational. The other thing to notice is that if that isn't exercises, but also a theorem of Sanov from 1955, is that if S is transcendental, then this does generate a free group. That's really not hard. It's another exercise to do for people interested in these things. But this has been around forever, that this thing is not free. There's some evidence that this is true. And again, Greenberg Shalom would say something about this. They would say that delta S is a lattice, it's an irreducible lattice in a product. And in fact, that delta S is more or less, it's commensurable to the group I get by SL2, taking SL2 of Z and then joining 1 over D, where D is the, is the biggest denominator occurring in S. It's the denominator of S if you put it in reduced form. So you get that this group generated by these two matrices is basically an S arithmetic lattice for free out of this Greenberg-Shalom hypothesis, when people have been asking for roughly 50 years if it's a free group. D is S equals C over D, where C and D are reduced. So some number of primes, and you get a lattice in some in a product of a real Lie group and some number of p-adic groups. Yeah, so and I will say that I'm not sure I know where this question really comes from or why one cares. The other thing this proves is, you can think of it in reverse, is this gives you an explicit 2 generating set for a finite index subgroup of this thing. There is in the literature an explicit 3 generating set for this thing on the nose, but a 2 generating set would certainly be interesting to people who study arithmetic groups. And so this Greenberg-Shalom thing just keeps connecting the things, and I could probably tell you 4 or 5 more, but instead I'll stop and let us end the day.
Questions for David? Is a lattice or?
No, I mean that really is somehow it's the most interesting part of the question. Maybe is that if it's a normal subgroup of a lattice, then we can.
Yeah.
But if it's just contained in the lattice, then we can't. And we can't, even if you assume there are things you have to watch out for. You can even assume that it's contained in the lattice and that the lattice is part of the commensurator, and I still can't prove it for contained in the lattice in general.
Okay.